All right, we're live for is it 7 now? Part 7 of our Synacor Challenge streams. Um, and where did we leave off here? So last time we added the ability to log instructions as they are running. So we allow in our shell to, well, we can do this here. Allow me to demonstrate. So we have op log toggle. So let's toggle that, see if it's on or off. Oh, no, sorry. Toggle op log. Um, hmm, okay, well, I've broken something. But anyway, we have the ability to toggle an op log and then record operations that are being run, and then show all those operations that are running. And the idea is that we can then look at this assembly that has been run between two states of interest, in particular the teleportation activation, and then try to disassemble that or read it and try to make some sense of it. Um, so for today, I think our primary goal, well, our end goal, the eventual payoff that we're hoping for here, is that we can extract these functions that are being called when the binary is running, and then try to make sense of it. So there are multiple levels at which we could extract it. Like at the very basic level, we could just show show what instructions are being run. So we've already done that. We can already go in and take a look at that, and I think we will do that for a little bit of a teaser. But what I want to do today is model our assembly instructions a little bit more because we use these instructions. Well, we now print off of it. We are extracting it. So we have a nice like toString, right? We're extracting it, and then in the near future we'll be injecting it. So for all of that, I would like to have a nicer, more coherent model, encode some of our assumptions, some of our constraints, some of the invariants that we've discovered about how the Synacor VM runs. And as I was saying, there are multiple levels of extraction that you could do. You could just read it. You could extract it into an actual like assembly instruction objects. But going even at a higher level, we could try to start creating a decompiler, right? Um, and at a basic level, that would mean identifying, like detecting functions that are running in the VM code and saying, okay, this is a function call. The function lives at this address. It has so and so many parameters, and then or now we could just show the bytecode and how it's used. But we could also try and like make sense of that bytecode and say like, hey, these variables are set using these expressions. So we can start to build an expression tree, starting by first making a function call graph and saying, okay, which functions are called, which ones are used in between two different states, um, and where do all those functions live, right? So what function is called most often? Where does it live? Where are the points of interest we would like to really disassemble? So that is the end goal eventually. Hmm. Um, diff2 states, this means there's many different things. So like there's diffing memory. Um, let's add new goal here. We want addresses of function calls. Um, let's see, functions, we'll call them functions of interest. And then we also want graph of function calls. And in order to enable this, we will need better models. So even above that, we have the goal. Well, actually, it's already here. Model of the assembly language. Okay. And then there's still this one down here. We can do a model of the assembly language. We can do a full-on AST for VM state transitions. And that might be actually useful when we start to make a proper decompiler. So um, that's feeling less like a stretch goal and more like a reality, a fun challenge. So goal after that, create a decompiler. Okay, so diff2 states, we'll just say diff memory. That might be interesting to us. We kind of have some ability to inspect state. We'll just cross that off. It's just noise for now. Um, this is just nice modeling. Disassemble bytecode into something readable. Um, oh, yeah, that is creating a decompiler here. And we can say let's say that's partially done because we've at least printed that. Um, I guess I'll go there. Okay. With all that said, let's go take a little sneak preview. Here's a teaser of what we're gonna get to. Let's look at our play worksheet. Okay, so here is some of what we found. Um, some of the bytecode we found running. So here's a return. Oh, this is actually just a subroutine. So some subroutine was called. And then we're doing more of these, reading from mem, and then we have more returns. There are no calls in here. So maybe this is less interesting than we'd hoped. Actually, there's a call. So call the function at R6. We push R2, that's parameter. Um, we set R2 to the value inside of R3, which is that value. Oh, that's interesting. Why would we push this value here? And then, oh no, we're pushing that onto the stack. So we're pushing R2 onto the stack. Then we set R2 there. And we call a function, and then we continue after we call the function. So after we call the function, we push these two registers, register values. And then we call these functions, we pop these two registers, and then we return. So this right here is what a function call looks like, right? So what does that tell us? There's a let's disassemble this into some pseudocode. We have def foo. We'll call them all foo. This is foo 0600 because that's the address at which it lives. um, uh, yeah, let's call it f0600. So this has two parameters. Hmm. So let's call them A and B. And what does it do with those parameters? So we push two parameters, R2, R2 and R3. We and R3 with R1. Hmm. So this is referencing registers. This is not just using a stack. So it's using something that's in scope. So we store into R3. Yes, Synacor Weekend Special, for sure. Sparkly Dark Matter. Hello, welcome, welcome. Um, so I don't know how much you missed the intro, but yes, this is an extra. I decided not to take a break for this night anyway. But that doesn't mean we won't be doing worthwhile things. So just now I was looking at a function call, at what that's structured like so that we can inform the wish list that we're making. Um, our broader goal is to get some sort of a disassembler, right? Um, and to be able to find these functions, we want to make a graph of function calls. So first, we have to find the functions themselves, extract them, get the addresses of them, and then we can make a graph of function calls. And then going further than that, we could actually try and start to create a disassembler. Um, Not just a disassembler, a decompiler. But first, in order to enable any of that, we want a model for our assembly language. This will already be useful because we're already doing a few things with assembly, so we're interpreting it for state transitions. We are printing it when we log our running bytecode. Um, and printing will turn soon into extraction. So we want a model to extract it into, and it possibly turns into injection. Um, so let's actually list this here. Printing, extraction, uh, injection, and then there's a interpretation. Interpretation. So that's the reason we're doing all of that. Um, and I figure while we're at that, we can clean up, we can clarify our model a little bit, and create more clarity. Right. So I wanted to leave a lot of code, make some invalid states unrepresentable, and give ourselves nice tools with which to think and with which to build fancy shit like a decompiler. Um, yeah, so in service of that, just making sure I'm not going down a wrong rabbit hole, I'm looking at some of the bytecode that we discovered yesterday. So this is bytecode that runs at some point during the um, teleportation validation. Hello, WFMK. Welcome. And I'm reverse engineering this bit by hand just so I know what a function call looks like. So we call this address, we push these two onto the stack. Um, so these are, I would call these parameters or arguments to the function. So this function has two parameters, an A and a B. And then it does these operations. So store into R3. So R3, I'm just going to say we're declaring a new variable. So val x. X equals the value of R1. Now R1 is something that was in scope. Blaze Bits, hello, welcome, welcome. Blaze Bits, how was your stream? What kind of a project were you all doing? I'm hoping there's a little bit of similarity and we can continue some assembly bytecode kind of stuff. Welcome, welcome, Raiders. Arno Gumby. Um, so this is the Synacor challenge, and we are given a binary that we are. Let me give you a link for the notes so you can read more about it. But yeah, the long and short of it is that we have this foreign binary, and we have an architecture spec, and we implemented that. We implemented VM so we could run the program, and it turns out we need to do some bytecode injection or extraction to make this work properly. To discover to solve the puzzle that's inside of this running binary. So we're building some tools that allow us to model that assembly in more granularity. So you were coding up an AI hacking bot to play capture the flag challenges. Okay, very cool. Yeah, it's a very fun project made by Eric Wastl, the creator of Advent of Code. Very similar to some of the reverse engineering puzzles he has put into Advent of Code in the past. So X, R1. R1 was never pushed onto the call stack, I don't believe. So there was this call. We pushed a value in R2. Yeah, so R1 was read from memory. So there was like some variable that was set previously. Um, I'm gonna give these a different naming schemes. So A we'll call our arguments. So we had A1 and A2 are the arguments. This is what was pushed onto the stack. And then X will be the variables that we create. So we're assigning something into R3. So we'll call this this is an X that we're creating. We can maybe we can make a variable declaration clause. Anyway, this is being declared and set to the value of R1 plus R3. So R1, since it's already defined elsewhere, we'll say that this is a variable that's defined in scope earlier. So we'll call that V. We're ending V R1 with a R2, which was which was pushed from the stack actually. Pushed from the stack. Oh wait, R3. We pushed the values of these onto the stack. We haven't popped anything from the stack. Let me just look at our spec. So when we push, yeah, we push a value inside A onto the stack. Interesting, because we're not popping from the stack. So we run through the function call, right? We jump to this address, and then at this address we are doing this stuff, and we pop R3 and R2 at the end. We never actually use the values. We just pop them and then we return. That's very curious to me. Oh, I suppose we are reassigning what's in R2 and R3. When we do this pop R3. So when we pop, remove the top element of the stack and write it. Wait, where is that? And write it into A. So we're writing into register 3. Okay, let's give these. We'll call this R3. This thing that we're setting. So R3 becomes R1 and R2, bitwise and then R3 equals not R3, R3 equals not R3, and then we R1 equals R1 and R3, R1 and R3. And then we pop R2 and we pop R3. So the things we pushed earlier onto the stack, we are... Okay, so we were saving these values before we call. And then we return. So hold on, what does this function return exactly? Because we push these values onto the stack, we do these operations, we change the values in the registers, and then when we return, we pop these two off. We could put in register names here for now. We're not going to try and disassemble that at a higher level. So we pushed R2 and R3. And then we use R2 here to reassign R3. That's very weird. So the end result of calling this function, before all this happens, we go R2. Oh, there was a function call right before that, FB. So there's an outer function that calls that. So maybe that'll help us get some clarity. So there is a def f. There's a function at 05fb, 05fb. And before that call, well, after that call, there's a single push. So we push the value of R2 onto the stack. So we'll just call that parameter A. So parameter A is set to R2, I suppose. And then we set R2. R2 equals the value inside R3. And then we call F0600 with R2 and R3, basically. So we'll say we do that with R2 and R3. We push those onto the call stack. So we push those functions onto the call stack. We set R2 equal to R3. Then in that function, we set R3 equal to some value of R2. So R2 equals to R3. So the A, basically from earlier. So these both would hold the same value. So we mask it against R1, which was defined who knows where, way earlier. And then after all of that, so after we do this function call, we output R1. So we output R1, which got mutated in this procedure call. Okay. And then we return. So I don't love this. I don't love that this function will just mess with whatever's in register 1. Right? My hope that was that the functions would push values onto the stack, maybe assign those values into registers, do operations on the things in the registers. Like the registers would be used as variables and just local variables. But apparently R1 is like a global variable. It's being used here as a global variable. Um, so pushing the value onto the stack, actually pushing the value onto the stack should mean like saving it. You save those values and then you pop them later. So when you push these values onto stack and then we pop them. So afterwards, R2 and R3 still the goal is that they still have the same value. So R2 equals R3. So after we call this, then we have R2 is still equal to R3. Okay, so the goal is that the functions of the parameters used by the function that is calling are not reassigned. So we push and we pop. Cool. But why does the call happen first? I mean, I suppose you could do it in either order. It's just that when we call, we go to this function location, and this function location here, f600, is the one saying, "Hey, I'm gonna make sure not to mess with R2 and R3," right? But this function doesn't know that this one here, this calling function, didn't want those to be used. Eesh. Okay, so I think enough of that for the time being. We at least know it's a little bit more confusing than I'd hoped it would be. Um, uh, and the good thing is we're about to make like some sort of function call graph, so we can find other function examples to look at and hopefully make better sense of this. And maybe if we can find like the root of some big function call graph, then we can extract something that makes a lot more sense than whatever kind of sense I'm trying to make of this. Alrighty. Um, so continuing on, in order to enable all this, we want a nicer assembly model. So let's look at our VM state. So this is kind of the core of our VM, right? This is the class that stores all of our memory, where our current instruction pointer is, the values in all our registers, stack, etc. This is immutable. So I create many instances of VM state, um, and then I transform it by making various operations to the registers, right? So I might move the instruction counter with by just progressing past this current instruction to the next one, or by jumping to a particular address. We can store in registers, we can dereference them, etc. And most importantly, we can this tick function interprets a single instruction, right? So something straightforward like add, we store into the value of our argument A, which we're interpreting as a register, the value of B plus C. And when we're saying B dot value here, this is something that we might dereference, right? B might be a register. It might be a literal value. So these are all of the state transitions, right? We store into A, B plus C, and then we move our instruction counter, and we have no output. And that is our tick. Um, and we are also showing these. So we have a way of printing these instructions. In fact, let me try and run this again. We'll get back to that in a sec. But let's run our emulator. Okay. So we're gonna start it by turning on the op log. Actually, no, let's not do that. Well, no, let's do that. So we start an emulation run, and before we do anything, we're toggling on our op log, and that will record these instructions as they're being run. So when it first powers on, there's a power on self test. So we're going to see instructions for that whole self test of all the opcodes. And this is our welcome message, right? So there's a welcome to Synacor, and a self-test complete announcement. So we have passed all the tests. So what ran there? So we have these commands. Let's look at the size of the op log. So 700,000 instructions ran. So that is way too many to show. But we can try showing them anyway. So show op log. And yep, this is everything. This is everything that ran. And you can see all these pops happening before a return. This looks like the end of some function call. And then it ends at this in instruction. So the very last instruction called was in, which means it's basically sitting here waiting for us to do some sort of output, some command. So I'll say look, and we're back at the foothills. Right, so let's clear our op log. Oops. Clear op log. And go back to our VM state. And I'm actually going to make a new file here because I want to model an instruction properly. So we'll call this well, if we just call it an operation, an op. Yeah, we'll call it an inst. Okay. In the same package, we have a case class instruction or an inst. An instruction has an argument. So let's see, let's look at an example instruction that's being run. Right, so well, actually the first thing it has is an opcode. So there's an opcode. You also need to import from numbers, import numbers dot star. So instruction has the actual instruction being run. And in this add case, there are 3 parameters. So there's going to be a list of parameters. But this is a running instruction. This is not a model of the like AST. So I'm going to call them arguments actually. So args, and it's going to be a list of args. So our arguments are words, right? So A, B, C are all words. But we have a couple of different ways to interpret them. So right, B is potentially a register, potentially a literal. So it's like a reg reference. So we can enumerate them this way. So we have an arg, and we have a case register reference, reg ref, and there's a register that we need to dereference. So that would be like the B here, where we might call dot value. And we'll say that extends arg, right? And then there's also potentially a constant. So B could have just been a literal. So we'll call that const. And then V is going to be a lit. Maybe, because we also have the same thing going on here with addresses. So B address, this could be a register that contains an address, or it could just be a raw address. So we can be saying read from raw address, whatever, or we could, so it's not just a lit, it's going to be some A, which is either an address, or we could do that constraint here. So we could say that A is either a lit or an address. Maybe we don't need to add that constraint, but it makes it clear to us for now. And yeah, we're storing that to A. So A is also a register reference, but in this case, we're not actually referencing it. So those are, I think, all our kinds of parameters. Yeah, those are the only ways that A is used. We all either do a.reg, a.value, or a.address. Yep. So an instruction that's run then is an opcode followed by a list of arguments. Now this list of arguments is at most 3. It could be 0. I might actually specialize that. Like maybe there's an uh, maybe there's like an inst 0, right? This has no arguments. And maybe there's an inst 1, which has just one argument, a arg. I might like that. We'll see. So B arg and then C arg. And what's going on here? We have like a little formatting issue, I think. Oh, right. This here is inst 2 and inst 3. Okay. And maybe these all extend inst. I'm still not sure which of these two models you want to use. So let's look at where we're actually going to use them. The first most obvious place is here in show. So here we're showing all these various instructions, and we recursively we'll show an arg. Show arg here means that it's a register or lit. So we'll want some sort of a show method for an instruction. And for that, we'll need to recursively have a show method for an argument. So I think it's time to, we can introduce a show type class here to say that something is showable. So trait show given an A. Basically a show, basically it has a toString method. So that's what defines that. So def show A of A, it's going to give us a string. And then now if we do, we want to give ourselves a method show of any A that fits in that show type class. So this is a context bound in Scala. So this gives us a string given a show instance. Actually, we're going to do it this way. Object show def apply A. So this will summon an instance of the show type class. So we are using show A. And then we'll do show.show our. Oh, no, we just do a summon. So summon the show A. So our show function, which will show anything that has a showable instance. Like we could rename this. You could rename that to showable. That might be more clear to some people. But we'll basically summon the show for that A, and then dot show A to get the string. All right. I know it doesn't seem right at the moment obvious why I'm doing that, but so that I can show things recursively. So for an arg, we'll also need a show instance. So how do you show an arg? You have to recursively show either the literal or address if you have those. So let's define how we get that show instance. So how do we get a show instance for an arg? We have to use with in this version of Scala. Given show equals, I think we can just do, we're implementing a show here. We have to match on this first. So we're gonna match this match exhaustive. Oh, no. Def show instance. We're gonna do it this way as an implicit function. And it gives us show for an arg. So we're gonna take A and we're gonna match that exhaustively. Reg, this is actually a reg reference. So in the case of a register reference, we would just take that register reg dot, and it already has a nice toString. So that will be the show method there. Well, we also want to dereference that and then show the value that's inside of it. So what we were doing here in show arg reg literal, if it turned out that that was a register, then we would show it the name here. The comment shows it, right? R2 followed by parentheses and the value that's inside. So you don't want to just do reg.toString. We want something more like this. Oh, we have a reg.name method. Okay, so we have reg.name parens and then the dereferenced value. And now the tricky thing here is that dereferencing this is contextual. So we need more context then. So whatever this register is a reference to, how do we deref it? We need registers. So we need to do like given registers. So using registers. So we need to do registers dot apply that index. So apply it reg. And then whether we do toLit or toAddress will depend. But at the end of the day, we're going to do like dot hex. So in this case, a regref does have a type. And this is going to be a lit or address, right? And I think what we might actually need is separate instances for a regref. So we'll make a separate function here. Oh, okay, comment that out for now. So def show instance for a regref given some type A. I'm just gonna go with show regref of A. And in order to do that, we need to know how to show recursively using a show instance for the A itself. So the val A is going to be, we do also need the registers. So we'll add that as another parameter. So we have registers and we have show A. So registers, we dereference that, register, etc. And then we do show A on that A. So inside these parens, we'll have show A of A. And this is a whole new show instance. So this is actually going to be like a new show. And this is the def of the show function, def show. In this case, regref. Gives us a string. And the string that gives us is exactly this. Okay, so this is a given def, given show regref. And we have an issue here. Ice Cold Witch, hello, welcome. And I'm doing. Oh, wait. I'm confusing myself here. Just given is fine. Um, and expected I use in here. I don't think we need to add this parameter. We do need the registers. So we're applying the regref here. The regref itself has a register, so regref.register. We found a word. We required an A. Right. Right. Eesh. Okay. So we need a way then to convert a word into. We need to convert it either to a literal or address at this point. I'm not actually sure here. Well, we don't need to derive shows fully, I suppose. Right, like we could still make this methods on the arg. And then once we get those methods working, we can make the given instance for this. If that's always going to be a word, show a, I guess, yeah, we just have the core issue here is that we have to convert word into a literal or an address, but we have to do that contextually, right? So it depends on the type of show regref. And we haven't implemented any kind of converters there. And I don't want to stay on this for too long. So I might table that for just a sec. And we'll just put it, we'll just do a toString method here. So toString equals this match exhaustive. Well, we could basically take these methods here and move them over. So an argument you can either show as a lit, or show as an address, right? And that's what these were here. So show arg actually should be renamed. We'll rename that to show lit. Show lit or show address. Reg or address, reg or lit. So that gets called on a word. It's like a contextual toString. How do we interpret that word? And I promise once this is wired up nicely, this here does simplify greatly. But for now, we'll have this, but it is implemented not on a word, but an argument. And what I think I want to do is take my A, B, and C. So A, B, and C are my three arguments, right? And they are um, they are the next. So opcode is at some sort of memory location, and then the next three memory after that are our three arguments. But right now we're extracting them as words. What I'd like to do is that, but we extract them as args. And we can't know the type of that arg just yet. but we can at least know whether it is a regref or a constant. So in the case then of a regref, I probably should start this top down because I'm realizing for an argument we just don't know yet if it's a literal or address. Because this can dereference. Now regref can dereference. So let's do that. Def deref given registers. And that will be to a U15. And this is once we know for sure it's regref. So here at this point, we know that's a word. We don't know whether that word is a register reference or a constant, but we can know by checking the 16th bit. Can we do this here? Actually, I don't think we can put it in there as a method. So we'll do this object arg def. So we can do like arg.deref, and there's a reg reference. And this goes to a U15. We could actually define this as an extension on a reg reference. With the method deref, which needs registers, returns U15. And if you look at our deref here, it is just using the registers. So we are dereferencing that register given those registers. And then we can parse this from Word. So def from Word. And we can have like an arg method. Or actually, you know what? These will all just be args. So this here can be something like arg.fromWord, and then we get the word that's at that memory location. Then we can match an arg and see if it's a reg reference, we do something. If it's a constant, we do something else. We don't anymore, I think, need parameters for that. And that gives us a U15, which we can then convert to a literal or address. And from word is going to look much like this here if it fits W15 or if it fits U15. W word. And this is going to be an arg. So if the word fits U15, then it is a constant of that word dot to U15. Let's look at our numbers. I don't think we have a method like that yet. So in a word we can add a dot U15. Def U15. And that can just be U15 from int. I'm not sure if we define that. Def from int. We defined it for word. Yeah, we have defined it for a U15 dot from int W. And in fact, I think, right, our dot address function just recalls U15. But we could also have, I think we'll need this for convenience, extension on a U15. So we'll want lit and address as well. Quantum Apprentice, thank you for the follow. So in this case, in this file, um, everything is actually an int, but these are defined as opaque types, right? So a lit is a U15, but it's backed by an int. So in this file, it knows that these are all the same type, and casting is sort of free, right? So I can say that number, and that will type check even though this is an int. But in any other file, these are distinct types. So this prevents us from accidentally doing things like multiplying by an address because that's not legal, or adding 15 to like some 64-bit number because that would also be illegal because we're supposed to be using only 15-bit numbers. And then so we have lit and we have address. Those are the only two ways to interpret a U15. And that gives us the casting. We say that's legal. And often the casting, like here, has to do a check that we fit in the bounds. In these cases, these are both U15s. Okay, so regref, regref.reg. Okay, we need to pass along the register there. So if it fits, then we do a constant dot U15. And this is a U15. And I'm still playing with the idea here of adding a type parameter. Because, oh, Quantum Apprentice, hello. Welcome, welcome. How was your stream? What were y'all working on? I appreciate it. I don't know if you've heard of the Synacor challenge, but it's made by the Advent Code creator. So it's similar in spirit. This is a big reverse engineering puzzle. We're reverse engineering a binary. We had to build a VM to run a program, and now we have to do bytecode injection and extraction so that we can reverse engineer that program, so that we could solve the puzzle. So we're doing that right now, and in the process of that, I'm kind of sprucing up my model more properly for my assembly instructions because I want to extract those instructions and play around with them. Yep. So you were working on a video player for Fallout's proprietary video format. Oh, that's fun. So you were doing some reverse engineering there. Why do they have a proprietary video format? What the fuck? That's funny. But cool. So did you have to figure out the format yourself? Were you able to find some docs? That audio is throwing you for a loop? Pain, a pain. So you're doing some bit twiddling, and we're doing some bit twiddling over here. Good. So we don't have to explain too much then. It's the original Fallout's from the 90s. Oh, okay. That makes more sense then. That's cool. So if it fits U15, we parse that word as a constant. Otherwise, we say that's a register reference. And the reg that we give to it, so we already have a way of interpreting, yeah, we just do word.reg. It's a reg reference with w.reg. We found a word. We required a U15. Oh, right. So our registers, when we first implemented our registers, we weren't sure. Let's look at this apply method. Why can't I jump to that? Oh, shit. Have I been overriding VM state? We never wrote a new file. um, right, we were trying to write like inst. Oh, right, we accidentally put everything in inst. So it is still here, but we've reversed the file names. So we're gonna do it this way. We're gonna cut all that. We're gonna go to that inst file and then cut all of the VM state stuff and write that. There we go. VS Code doesn't get happy if you just rename the files. Definitely a little oopsie. The compiler was happy with it though. It doesn't care about the file name. Okay. Anyway, we were looking for VM state because we were looking for our registers. So registers are just backed by an I array, an immutable array. An immutable array is actually just an array, but it's like a very thin wrapper over an array that lets you use an array, but gives you the promise that you're not mutating, so you don't have to do defensive copies. So this apply method should actually just return a word. Or it should actually just return a U15. Yeah, it wouldn't make sense to the things that are 16-bit are like the register references. And it wouldn't make sense to interpret that. I kind of wish our opcodes also had that leading one because um, you can't tell that an opcode is an opcode just by looking at the byte. It could totally be a literal address or constant. So yeah, this is going to be U15 now, and we'll fix the fallout from that. Underlying is a vector of words. We can make it a vector of U15 now. Um, does that still work? Underlying the updated. When we update, it's going to be with a U15 word. I don't think this should break anything. Code versus data, code as data, exactly. Okay, so now this should work properly. Found word required U15. Dot reg. Oh, right, registers. When you call apply on a register, yeah, you get a U15. There we go. Oh, I thought we just edited this. Didn't we edit this? Interesting. So underlying. Am I going crazy? Weren't we just editing this file? Okay, so the underlying thing here is a U15. yeah. I don't know what happened there. So when we update with a U15. All these values here, when we apply our U15s. And then we do word.fromInt dot U15, I suppose. Okay. All right, the spec doesn't exactly specify it, but we've decided that registers hold 15-bit values. We'll want to run that and make sure that is actually true. In fact, we could, let's get to a compiling state so that we could do that. We're not actually using all of this new stuff yet. W.U15, W.reg, okay. Okay. This here, definite. Oh, Okay, let's not use these just yet because those are problematic. Right now, those compile to the same thing, to the same method. Or when once the types are erased, because these are all opaque types, they have the same signature and name, which means it's a duplicate definition. But we will want something like that. And I suppose since a U15 is a word, then it already has that method on it. Okay, yeah, so there's actually no need to even define these. All right, this show. Oh, given an A type. And A of type A. We summon a show for A and we call it show method. A that has a show. There we go. And this is, again, in service of making this instruction. So we're going to parse things out as proper instructions and not just a string. Because when we're printing this to the REPL, we're just printing strings. So we're going to make an instruction object that knows how to print itself and knows how to do any number of other things. So are we in a compiling state? If we're in a compiling state, let's see that registers can be U15 and not be an issue. We do have to go to VM state, def a. Okay, these three we are not using yet, but we are going to replace those. So I'm going to comment that out for now. Okay. Right. We created, let me construct the memory in the first place in main. We assumed that they were all words. So where is that? Val memory. A.2 vector. So when do we get the actual words? We do word.from bytes. Oh, hold up, hold up. Remember when I thought I was editing the same thing twice? Memory is definitely still U16, so memory definitely should still have words. Yeah, I had edited memory when I intended to edit register. So this is a word. Let's do some find and replace. U15 replacing with word. Okay. Class memory. This can just be W there. All right, a memory is still a vector of words. It's the registers that are U15. So let's make sure we're compiling. And then we update registers. So emu, in main here, we have a method that lets us get a register and then set register. And those two methods should now give numbers at U15. Register to register. Okay. All right. Oh, let me just have that run automatically in the background. If you put the little tilde there, then it tries to compile every time you save. Okay, but the current issue was in main when we're setting register, we're setting it to a word value. Okay, so when we set a register word from int, this is actually going to be .u15. So word, we're going to rename that to u15. Okay. Okay, great. So it ran, it made it through the self-test. I think we're cool. Yeah, I think we've definitively determined that registers are in fact U15 and not full 16-bit words. So that's good to know. The spec really, I don't think it makes that clear. So like when we set A to the value of B, I guess this is a clue here, because if B can be a literal or a register, right, if we were possibly dereferencing a register, then this could never be a 16-bit value. We can only ever set it to U15. And when we store into A, the remainder of, right, when you do math expressions, that's always going to be overflowed. So it's going to be masked to U15. Yeah. I think that actually does make sense in retrospect. Okay, so now we're about ready to replace these methods that give us words with these methods that give us args. And how do we use this? Here, when we're implementing our opcodes, we either say .reg, .value, or .address. And I think we still want that. So store. When we store, we do want the register. And then we want a dereferenced lit. Okay. So let's go back to that instruction here. We can make methods def lit equals this match. So in the case of a reg reference, and I think we need registers. So using registers, apply to R, that gives us a U15, and then we do dot lit. And in the case of a constant, we just do v dot lit, right? Now, I don't like that these are contextual. I think the interpretation of this should actually be kept only in VM state. So I suppose they can be extension methods here. So where are we dereferencing? Here's all the show stuff. And here's the deref stuff. Yeah, so this is the previous thing that we were doing. Extensions in a word to get the value address. I think we will instead do extensions on args. So extension a arg, and then we can give them the same name, value, just to ease our transition. Value is going to give us a lit, and it's going to do a arg match exhaustive. It's actually going to be exactly this method here. So a match a.registers.lit, and then no, we just do registers. Right, now registers is in scope, so now we can actually do that. And then we need a same thing for address, def address. And again, it's going to be a match exhaustive case. In this case, we do registers, reg.lit. And in the case of the value, just interpret that value as, no, not a lit, but an address. Okay, cool. I feel like this is starting to snap together a little bit. And then we don't need this deref method. But it was inaccurate anyway, because you don't deref a word. You dereference an argument. In fact, this regref could have a deref method, and we could actually use that in here. So if this is a regref r, it's like r.deref using some registers and convert it to a lit. Let's do that real quickly. I think that'll make it pretty. So extension on r regref def deref using registers. Uh, and that gives us a U15. Oh, wait, hold on. Did we actually, yes, we already implemented that. Great. Oh, well, I guess it's a good idea if I had that idea twice. So r regref, we can just do r.deref using registers, and then .lit. I guess we don't need to like fully even match on it, right? Just do that. Like that works. Oh, we don't have that in scope yet. Interesting. Oh, arg.regular. Yeah. And then this is an arg.const. Like we could write it either way. I think I do prefer matching on it this way. I'll leave that there just for reference for right now. But the point is we have a deref method in the right place. It's not dereferencing a word, so that makes me a little bit happier semantically. And now these show lit methods, those will instead need to be shows on instructions. And because an instruction uses an arg, we don't need to have this reg or lit, right? Uh, like here, I didn't like this because word is just word is just an int, and then we know something about word. We know that it's actually an argument, which is either a register reference or a constant, but our type system didn't know it. So we were writing the name of the type into the you were writing the types into the name, and then we were hoping we didn't mess up when we wrote this code, which actually we did end up with some bugs in here, right? There was some time. Yeah, we did end up with some bugs. Because honestly, each case should have its own show method, right? And you shouldn't have to uh, interpret it using this, saying like, "Hey, we're gonna say that this is so and so," and then you call that. We'll just already know that so and so, and then we'll be able to call show no matter what it is. But for now, that is not compiling. So let's comment that out, and we'll stop about this def here so that the compiler stays happy. Um, and great, now we can change our methods. So wait, dot value should still return a lit. Value.value is not a member of Synacor.word, right? Because these are no longer words up here. These are going to be arguments. Okay, and now that should compile. Dot reg. Um, I think we need to say that we are interpreting that as a register and then throw an error. Yeah. So let's call, oops, delete something there. Okay. Let's go back to our instruction and we'll do a def arg. Let's say to reg. I know we've been writing just reg everywhere. Here's my naming convention. Like, if it doesn't need any checking, if the cast can't fail, I might write as reg. If it can fail, I might write to reg. And then I might also write to reg option, which optionally returns a register only if it's possible. So we'll leave that there as a type signature, but we'll also leave to reg equals this match exhaustive. And in the case of reg reference, we just return that reg. And in this case, we throw a new exception, or we can just take v, and since v is a U15, which is also word, we can just do v.reg and let that failure happen there. Now I know I said to reg and all that. I'm gonna name it reg for now, just so that it does just so that it continues to compile over here on this side, because here we had written .reg everywhere. Okay, is this in fact compiling? Not found dref. We're using dref somewhere. Reference a word on the output. Right, when we output, that should be a register actually. So let's go to where that's used. We output. Here we just passed a along as a word. I don't like that. We need the argument. And let's say that that's a register right here. So a.register. Because if you look into the spec, that says the value of A. And I guess this is never done with literals. In fact, let me just double check the register. How to output a register. Arc spec here. Out. Write the character represented by ASCII code A to the terminal. I think that actually means this should be a dot value. Interpret that as a lit, maybe dereference it. So yeah, we don't need to be dereferencing here. Let's make sure that actually works. So we'll say just v lit and v.ascar, or n. Been using n by convention. And does that give us other compile errors? Okay, so when we store, a store method requires a register and a lit. So w.value found a word required arg. Oh, so this w here needs to be interpreted as an arg. Ah, that's interesting. Let's look at pop and see if maybe we don't have that want to have that return an arg. So like it does just return a word, but we want to interpret that as an arg. So we're going to do arg.from word w.value. Okay. Now when we update again, yeah, we're just taking state. I'm going to make this multi-line here just to make it a little bit more clear. So we'll make this word, and we'll make this state. State.update again. We'll take that parameter state. And then after all of that, we progress with no output. Okay. I think that works. And I think there should be one more case that's similar to that, w.address. So word.from arg. There we go. Oh, no. That's arg.from word. Okay, and error overriding method reg in class. Oh, right, registers already. Well, this is now to reg, I guess. And well, I'm just gonna go ahead and implement this option version because it's not hard. And this case here is just none. Okay, in case we need that, we've got it. And this actually could just be to-reg option dot get. all of the dot reg becomes dot to reg. Cool. So a dot reg is gonna be, oh no. Just all the dot reg dot to reg. That seems fine. Not that case. How do we skip over? Right, we're still doing that. To reg, to reg, to reg. Okay, cool. Now, great. I think we're happy. An implication is missing in our main method. Let's see. We did a triple question mark somewhere. Wait. VM state 150. Where did we do that? 150. Oh, right. Our show method is not working. We'll just make an empty string for now. I just want to see that everything else runs. Cool. The power on self-test still works. Okay. Now I think we can go to implementing our show. So we can implement show, but what this is doing is just taking the current thing and constructing a string. And I don't want to construct the string anymore. I want to construct an instruction. So what this will be, we'll do like def instruction inst equals yada yada yada. And what I want to replace show with is something along the lines of inst.show, right? That's my end goal. All this commenting code gets kind of replaced by that. Yes. I like inst better. But the inst, I think, will have some commonality with this implementation. So let's at least uncomment that. Now, what we're basically saying here, earlier we were saying like, oh, these things have similar toStrings, right? We're constructing similar looking strings. But now what we're going to be showing is that, hey, these things have the same argument format. So in this case, then, push becomes inst1, where a is a literal, a dot value. Well, we don't want to do a dot value because that dereferences it. So in this case here, when we do show literal, we say that this is a register or a lit. Right now, in our case class, arg, we have register or an arg is a register or a constant. So that or U15. And I think we already want to know at this level what kind of we're constructing. But again, an argument is contextual. Right, so we run into the same thing that we were running into earlier here when we were creating this show. So A is an arg, and basically we want to do like lit arg, or we basically want to say A, and we want to say, I don't know, like as lit arg, something like that. But also like maybe we want to do that at a type level, right? Like just as, I don't know, lit or something like that. Because it is important for how things are recursively shown. We'll give that name op because an instruction does start with an op. And we need to specialize it. Okay, so what I'm going to do then is I'm going to try type parameters and see if that doesn't get us into some sort of trouble. Comment out this reference code for now. We can actually just delete this. And let's give args a type parameter. So when we do like word to register, or like an argument to a register, we just never do it based on the value. We do it based on the context on what is being asked for at that moment. So when we were ticking along, we were doing that by saying like b.value. We're saying here that it's a value, but also we have a type, right? Um, we are storing a lit, so it should just interpret b depending on the type that's desired, right? So something like val x of type lit equals an arg b dot I guess that value, right? So like we deref that or that value, and that gets like the register value of that. So this dot value method then takes a type parameter, and that type gets inferred to lit. So we have value and address will both be one method. Value and address will both be one method. That takes a type parameter. So is that possible to do, or do things get erased? I want to avoid having to type in that guidance if I don't need to. Where's value defined? Just go to VM state. Actually, you know, I think I would like to save a commit. And I might take a little quick detour and clean something up before I get there. But I'll do all that when I get back. I gotta take a quick water break. All right, we're back. So we want to implement a generic show with like ad hoc polymorphism. But before we do that, I want to save state my repo. So let's fix some things I want to get in before. Let's look back at our ticks, right? So this is what every step returns. So this is basically what's a possible name for this? This is tick result. Because once you tick, you don't necessarily get to a new state. In the case of a halt, there's no new state. This here is a lie. This state is like the previous state. That's what we're filling it in with, but we shouldn't have that. Input, this state is also the previous state. There is no next state, not until we get a character. So this input says we're waiting for a character, right? So if this tick was like an option, then halt is our none case. Output is a some case. There was in fact a next state, and hey, that next state also had bonus output, right? um, and this is just like our sum, and input is like actually what we're giving you is a partial function, or like we're telling you how to get the next state. We can't get it yet, not until you give us a character. Um, Luckily, I think we're not using this state member, so let's delete that. So there should be none in halt. Output gets that, but we don't need to override anymore. And input shouldn't lie. We want all of our types to be honest. Okay, and let's fix the fallout from that. So there are places where we create an input. So like def input. This no longer requires this. As a bonus, we get to remove that unsafe ready. And then there's a halt, def halt. You're also doing unsafe ready there. Yeah. Better not to do unsafe things. Yep. And now show inst.show. Oh, right. We're going to leave this commented out until we actually have an inst in the first place. Okay. Our next thing, okay, I take the halt. Right. We can just give our exit code. And in our emulator, now we don't need to use the state. We were never using the state. Like we shouldn't be using that state. And our state goes from tick to tick. Our emulator goes from tick to tick. I'm not sure that's actually what it should be doing. I think perhaps you want it to go from VM state to VM state. So we'll leave that as a note to do. Maybe progress from VM state to state rather than tick to tick. So our history should be states. History should be VM state. But we will get there eventually. I was thinking about that earlier, and I think that will be nicer. And I'll show you what I mean in a little while. Okay, take that input. So when we set registers, Okay, when we set register with tick.input, we could actually still end up with a new tick. So here, what I done was I take the tick state and we do copy whatever. I think we just need to replace the function. So we do a new tick.input. And now this here, you have a tick.f. We could just pass along that f, right? But after, so this takes a character. We pass that f to the character, but after that, we have a VM state. And now in that new VM state, we can do dot set registers. And we pass our new f function. Or hold up. Yeah, our f function, what is this? Okay, yeah, so tick.f is actually just, it's a different function altogether. It is character to state. And we pass along our f here, our register. And that is our new tick. Cool, so we didn't even need to have access to state in order to set the registers. We can just we can just compose a new function from the tick.f. In fact, there's function composition combinators in Scala. What we could actually do is tick.f and then and I guess we have a function and then underscore dot set registers with f. So do one function and then do another function. I'm not sure. Set register is not a member of car. Okay, and then it needs to take VM state to well, set registers equals. We want this to be a function from state or like a VM state. Oops. And we do VM state dot set registers. That okay, so and then set registers. So the old take.f and then we do set registers. So and then requires a function from VM state to some a. Where I guess in this case it is going to be another VM state. Oh, right, type parameter t there. And I guess it depends on whatever the VM state was. Okay, that's going to be from a ready. So it's going to be a VM state ready. Dot set registers. That's the idea anyway. So VM set registers is non-method. Oh, okay, that's why everything's failing. VM state doesn't have a set registers function. So that actually be like VM.copy registers equals vm.registers dot set dot. What was my set registers function that we were doing before? I guess just f applied to registers. F applied to registers. Okay. Okay, now we should just be able to say and then. So tick F and then set registers. So okay, we found set registers, which is a function from state to state. This should return. Let's give this a explicit type. So this is a VM state ready to a state ready. VM state ready. So we take that VM and we just copy. So that's a function that we're passing along. Tick F and then set registers. All right. I think I'd like to have inside of my VM state more combinators for mutating that. So VM state should have a set registers function, or you could do like with registers or something like that. Bob, no. Hello. No, I wasn't gonna stream tonight. Well, I was gonna maybe stream tonight. I reserved the opportunity to give myself a break. So you haven't missed too much. The main goal tonight is to solidify our concept of what an instruction is. So we are implementing this here. So an instruction is an opcode followed by arguments, where an argument can be a register reference or a constant. So we're formalizing this. This is stuff that we already sort of kind of know, but wasn't all that formal yet. And part of the reason is, so in our show methods, like we do a lot of guidance here, right? We say that this is a word. What it actually is a parameter or an argument that could be a register reference to a literal or just a raw literal. But we don't actually know that. All we know is that it's a word. So we do like a lot of if else stuff, a lot of casting, a lot of like stuff that's unsafe. So that's part of the reason. But the other part of the reason is we want to do other things with instructions, right? So we right now we're just printing them. We're printing strings of them, but we also want to interpret them. We want to inject them. We want to extract them. And eventually we'll do extraction like this. Like this is just a string, but we'll do extraction to proper instructions. And this will allow us to build like a function call graph later, or to do a proper disassembly or reassembly of instructions, or injecting virtual instructions. So the payoff is going to be tomorrow when we go back into this and we start messing around with the instructions that are being called and looking for all of the call instructions and building a function call graph of the Synacor VM, and like saving the addresses of all those functions. Yeah, so today we are playing with semantics, a bit of a refactor and cleanup. It's not just a cleanup. It is saving what we learned before we forget it. We're saving it, we're writing it down into the type system. And yeah, this is actually already all changed. So this code looks similar to what it was before, but now B is not a word, B is an argument. And value here will match on, oh, well, that's not currently compiling, but yeah. And in the meantime, I was also cleaning up another bit of my model. So ticks don't always have state, because sometimes a tick is kind of a pseudo state. It's like an incomplete tick, particularly in the case where we need a character input in order to calculate the new VM state. Uh, so we're making sure our model is honest there, and that means an input tick doesn't yet have a state. So get register. Where's get register even used? What you're actually getting a register from is the most recent state. Okay, we could do a hack here. We could do a hack here just for the sake of time. In the case of an input tick, there's no tick.state, but we can do tick.f, pass along a space character, and that gives us a state, and then we can do .registers.ref to do his hack. And okay, we're back to compiling. Wait, are we? No, we have new things. Missing type parameter. Oh, we started adding a type parameter. We're not actually adding that just yet. That was just me talking. Okay. Great, and everything is still working. So let's, oh boy, get to see how dirty my AOC repo is. I want to save at least that bit that we had changed. So we'll save that note. We'll save what we did to the input tick. So I'm using maggot here to choose my patches. Stage that. We can stage this. Stage that. I think we'll want to change some things in main as well. We don't want to change that yet. We don't need to change anything in main or in our play worksheet. Yeah, we don't need to change that. We don't need to change that. But we do need to change some things in our VM state. We'll save that later. We want to change our tick definition here. And in the places where we use that, when we output, no, that's fine. Input. This is actually two diffs because it would just be a.reg, but I don't think we mind if this doesn't compile yet. Yeah, it still gets the idea across. I could always rebase the history later. We're not gonna do that now. Just getting things out of here that don't need to be here. Halt only takes one parameter. And I think there was another place where we had this exit code. This exit code is now safe. Okay. So let's commit that saying, be more honest about tick type. And then let's just do all the changes we've done so far. So these words are now, I guess I don't need to comment that out. Def A. Lazy Git is awesome, but you have to find a more convenient. um, I'm not using Lazy Git, but is it similar to Magit? Because that's what I'm using that from Emacs. It's a great tool. We had like a def A somewhere in here. Yeah, we don't need these comments anymore. That's the change there. So let's go back to Magit here. All right, so this change is basically what we just did right now. We're using args instead of words. We don't need to comment out that show yet, I suppose. But we do want to change stuff here, how this is used. Okay, so the only text that changes was a.reg, now it changes that to 2reg, but the semantics here changes, right? All those calls to a.value are actually now on args rather than on words. And I believe that has some associated changes to main right down here. And of course, there's a new untracked file, which was the instruction. Here we go. All right, so let's look at our stage changes for this. So there's a new file. There's commented out stuff that we don't necessarily need yet. Let's unstage that bit. Can we actually unstage a partial file? No, we can't. Okay, so there's a new file. We have those bits. So this is the other big thing we did today. Use arg type instead of word to enable parsing to instruction. And Bob mentioned LazyGit. Haven't used Magit yourself. Oh yes, Bob Knoll. No, I'm not familiar with LazyGit, but I imagine it's somewhat similar. Magit is really nice because I don't know. It lets you do everything a lot more interactively. Like here are all the commands I could do. Right? If I type question mark, I can get information on how to run all those commands. If I were to do like, let's see, if I were to do a rebase, it gives me all these arguments here. So I could say like interactive, auto squash, or whatever. And it's like easy to explore what Git does because then I could like type question mark, type an argument, and it'll tell me like, hey, this is what this thing means. It's like your docs are into there too. Um, but like if you have everything memorized, you just type a few characters, right? So if this is push upstream or like a force push or whatever, it's like -fu or something like that, right? So very very quick to work with, very friendly for doing rebases and fix ups and things like that. Is there anything I missed from Emacs not present in VS Code? Yeah, there is a lot of stuff I miss. So I miss Maggot, of course, and org mode. I miss oh, what's the name of my find tool? Like text search is easier, and that is probably fine in VS Code. text search, macros are nice. Um, Find and replace with regexes. That was something I used more often. I don't have a replacement for that yet in VS Code. And I really miss the model of Emacs execution, where like you basically have you have like a frame, and you can open that frame from multiple like a frame looks at a file, but you can open that frame from multiple different windows. So VS Code, I'm stuck in one window. Um, in Emacs, you can run it in like daemon server mode and like connect multiple uh, daemons. Here, if I split the screen, this is two different frames, whereas like in Emacs they'd be connected. I don't know if I'm explaining that properly, but the whole kind of model I miss. In YSAP's chat, I mentioned I do type-driven development. Is that common for Scala? When you search for it, Idris comes up. Uh, it's somewhat common for so like Idris does type-driven development. Yeah, so it is common in Scala. It's not like day to day in Scala. So it's more common if you're like a Scala library dev. So some of the same ideas in Idris doing like type-driven derivation is very common in Scala. So for example, I don't know, let's say you have like a case class and you're like serializing this, right? So you have a point with x int, y int, or something, and you want to like derive derive some sort of a serializer. So like def encode some point. Let's say you want to just have a method that encodes anything. So you say encode a value a of type a, as long as that a has a encoder, right? Um, and then there's like a derivation for an encoder of a point that basically gives like a type-driven macro. It doesn't need any reflection. So reflection is runtime when you're inspecting the shape of a class, but derivation is compile time. So basically, I would construct an encoder for a point if I have an encoder for both an int for the x and the y for all of its parameters. And if you have a way to compose that, then you can have like very deep case classes, and you could serialize to JSON or something like that for essentially free, right? Like basically at compile time, the value is constructed for you of the serializer or deserializer. So no runtime inspection and no like runtime construction of those. So that kind of stuff is very much type driven, and it is culturally a thing in Scala. So like I know like Idris is on my list, is on my to learn list. I have the book Type Driven Development in Idris. I've started reading. But yeah, we do some type driven development here. We're at least gonna do type classes today with a show instance. Um, anyway, what do we need to do now? We still need to implement all this show stuff. We need to implement this instruction stuff. And in order to do that, we were considering what happens if our arg has a type parameter. So in this case, arg, yeah, this is an arg of a, and there's a red reference of a extends arg a, and a constant a extends arg a. And A is usually going to be a lit or an address. You're trying to map in your head to Rust, which seems to have similarities. I haven't looked into type-driven development, though. Yeah, Rust does have some similarities. Rust traits are kind of like type classes. A trait in Scala doesn't mean the same thing. I kind of wish Rust had named it something else because it's confusing when you're talking about it. Because trait is used in other languages too. Word trait. That means something more like interface or class. Okay, and the whole thing that's motivating this, if you take a step back, instruction. Um, right, so we're doing like a match on the op, and in this case, for push, we know that this thing here needs to be a lit. So we could say that that is right, something like that. We need to give it the type information there. But then what is the type of this whole thing? So I guess an instruction has types for each of its arguments. So an inst1 has like an ABC. Let's do this here. Actually, give me just a sec. I'll be right back. I need to make sure I have my earbud chart here. Okay. So inst1 has one type parameter A. Inst2 has B, and inst3 also has C. Um, and then each of these args themselves then have types. So arg type A, arg type B, and this becomes necessary if we're going to pass this along. I'm still kind of worried about type erasure. I haven't thought all the way through this, but we're discovering it. We're figuring this out. And maybe we do just have to do something similar to what we did before, where we assert the type, or we do like a cast-ish thing. And that is pushing me away from this model here, where it's just a list of arguments. If it's typed, it has to have those three types laid out. But we do have, let's have a sealed trait inst. So all of these extend inst, and I think they'll need to pass along the instruction. So an inst has an opcode. Oh, does that work? Okay, yeah, I think that works. We always have to know an inst's opcode. And maybe an inst has an opcode Maybe we save the type of the opcode in there too. We could do something like this. Inst has a type parameter O, which is a subtype of opcode. So this here is an O. Maybe. I'm not gonna say that just yet. And now in order to replace our show methods, we have showLit and showAddress. So we basically kind of have like a show arg. Well, this here is going to become inst.show, right? And an inst.show. Let's try to implement an inst.show, which will be inspired by this. Let's move this over. Okay. So there's a def show in all of these, but they're going to look different in each of these. So in inst0, we have def show, and it's just going to be the opcode. I think we'll want. We had addresses over here. Let me see. Show oplog. Oh, what's going on here? We messed up our input. Oh, right. We're not compiling right now. But anyway, we were showing the addresses in front of each line. I don't think we're going to do that here. What we're going to do is like pair this with that, because I don't think an address should be part of the instruction. Right? We could have a map of addresses to instructions and print on each line the address and then what instruction is at that address. So this is just opt.toString. F show string equals opt.toString. But now if we're doing something like this with arg-a, then the definition is going to depend on a. So def show a will need to be able to show an arg-a. So it's going to be op space then a.show. So we need to implement then a show on a. Okay, so let's go to arg. And let's define a show here, def show. You also like darks. Okay, so there's darks, there's lazygit. Is lazygit VS Code based? And there's maggot. I'll be curious. I'll take a look at those eventually. Okay. So this is going to depend on the A. So in either case, this is where we had this toString here. So we were doing something similar here. So first, it depends on regref. Let's see. Let's just do a method for showing regref itself. Or let's do one for showing a constant. So def show constant of type A. How how do we do this? Well, it turns out I guess we need to be able to show um, a literal or an address. So let's first do that. So what we're kind of doing here is we're manually going down and doing the recursive construction. Um, and then after we do that, we can take off the actual definitions here and just turn it into like an implicit engine and show how the derivation there works. Darks is a different VCS. Oh wait, yes, darks is it's used for Haskell, right? Or in Haskell projects. I think Xmonad uses darks. I can't remember. Yeah, I have heard of darks at some point. Okay, so in order to get that, we do actually have we do actually have a type class for show, so we can at least implement this for lit. So given a show of a lit, how do we show a lit? Um, equals wait, I think we do with. So this change between Scala 3, 5, and 7, it's nicer now. I think ideally we could just say colon, but with def show, um, a is a lit in this case, and toString, this is pretty straightforward. It's just going to be a dot hex. And then we can give ourselves a show instance also for an address. And it's a dot hex, but I want to see in our VM state, we didn't just print it that way. We can uncomment this because it still actually runs for now. And in fact, I don't know, we could straight up uncomment all of that too. But when we were showing a register address, we prepend at on the address. We could say that it's a pointer. Does it make sense semantically to prepend an ampersand to that? I don't know. It's been a while since I think I've thought about pointers. So this could be like and a dot hex. Show an address, show a lit. Yeah, if you're doing a literal address, I'll take feedback on how that should be displayed there. Okay, so now in order to print, in order to show a constant, let's see, let's make sure that compiles, right? Yeah, we're happy with that. Let's fix any other things, missing type parameter for regref. Yeah, let's fix that. So extension on regref, it needs a type parameter. So given an A, dref should work regardless of that. So this actually can just be a question mark. This can also be a question mark. a.shows not yet a member of Synacor.arg. Yes, we're going to implement that in a bit. And we are missing type parameters all across the world here. And I think it depends on whatever type is inferred. So whatever A is there, it's going to be arg of that type. And so now arg.fromWord needs to have a type parameter. Okay, so this has some A. And now we need evidence that we know how to instantiate from a word. So I guess we need a new type class here. So I don't know, construct, or, maybe we give a cast type class. So if you can cast something. So what is a cast type class? This is recursing a lot. Let me catch up. You was reading the README, and it's funny they mentioned darks as rigorous or backed by formalized theory, where in reality it still work still has to be done with respect to formalizing. Fair enough. What kind of work do you need to do, like, with formalizing? I'm not sure in what way darks is. I mean, I believe that they probably went about it with a principled approach. So def cast t, and I guess this just means we have a way to get from a word. So we can cast a t, gives us that t, right? And we're gonna do something similar. Let's put that closer to our show here. We're also gonna have a way to summon that. So apply a given show a. We can say, oops, we can make all our generics a. So this is just a convenient syntax for summoning a cast, which is to say, like, if there's an instance in scope, we use that instance. Which is to say, like, we can only use cast contextually if the information that's necessary is within our context. So using cast type A, summon cast. Okay. But wait, what does a cast actually do? So let's say given cast of a lit with def cast, and it's just going to be word to lit. So then this is actually a function word to a. So in this case, def cast can just be dot lit, yeah. Def cast. I guess let's give cast a parameter. So there's the word that's being cast. W word, and it's gonna be word dot lit. That's how you get a lit. So cast is a function, has a type parameter a, and you cast a word into an a. So that's our cast. And this is how we implement it for a lit. And this is how we cast an address. W.address. Okay. Now that we have that, I see the shots fired call. I'll catch up with you in a sec. Now that we have that, what were we actually trying to do? We were trying to show, we can't show this yet. We're trying to show an arg. Or I think it's even narrower than that. Oh man, my stack call is overloaded, my mental stack call. Okay. Here, showing a constant. This is it. So in order to show a constant, we have to have a way to cast a word. So we need to be given, or no, we're using a cast of the type A of that constant, and we're also using a show of that same type A. So now to do this, we take constant, that value, which is a U15, and we can cast that. So let's summon our cast of A, dot cast on the constant. Now that gives us an A, and then I'm gonna name this here actually show const. And now we had a generic function here. Here, this shows anything. So it shows anything as long as there is a show instance for that thing. So cast allowed us to convert something into an A. And we also asked that our A has a show type, class. And so now we can do show cast.cast that. Not found type const. Arg.const. Okay, yeah, I think that works. And I think we can do a similar thing here we did to the cast. We can give a method here. And I'll probably move these to their own file. So def cast a given a cast instance. And that gives us an A, and we do, we basically sort of implemented an implicit conversion. Except it's not, it is explicit. We are explicitly saying cast. So cast a dot cast a. There we go. Oh, no. Cast a word, W word. And we cast a W. There we go. So that's how we cast, that's how we show. So now this show const. So when you show a const, you basically cast const dot value, and then we show that. Okay, so we have a way to show a const, and then now we want a way to show a regref. So def show regref, and again, it has a parameter. So there's a regref of type A. Now here I'm going to show context bounds. So we could say, ooh, I think this is the syntax I don't have yet. We could say that cast is in those bounds. Yeah, we got cast and show. But we don't have that syntax. So what we'll say is, we'll just copy this here. Using cast A and using show A. And now this is going to be a little bit more complicated, because this is going to be like, where's the code that we copied? Like this here. Okay, so when you show a regref, if it fits E15, we do that or whatever. So that's a whole arg. This is actually showing an arg. So we're only interested then in this lower line here. This is the else case. We basically take the regref's name. Regref dot reg dot name. Yeah, we take the name and then we have parens. And then inside those parens, we then take the value inside of the regref and we show that. Now that value inside the regref is going to be U15. Actually, it should be an A. Right, so in our implementation here, regref.value needs to be shown. So we recursively show, and this is show lit or show const, but we have implementations for both show lit and show const. So we can just show that. I mean, show lit or show address. This thing is not an actual thing. Okay, so we have a way to show a regref, and we have a way to show a const, which means now we have a way to show any arbitrary arg. As long as we have the type there. Whew. Okay, we're making progress there. I know it seems like a lot of work, but I'm making it more work than it needs to be. And it saves us a lot of work in the future, and not just work, but it gives us more clarity in our model. It gives our model more granularity. So we were talking about darks. There's performance issues with the current model. Some algorithms end up being exponential time in the worst cases. The newest model that's currently being worked on and has been improved to polynomial worst case, but still work in progress. And JG mentions darks as an inspiration for a feature they call first-class conflicts. In reality, this is actually a weakness of darks. Oh, TB Josh, hey, you've been working on your implementation. You tried converting all the opcodes into instructions, but then I saw that there were random values in the middle that aren't valid opcodes. Fair, yeah. I mean, the thing about opcodes is they are only the values 0 through 21, right? So they look You don't have like a leading one or anything, so you can't look at a random word and say, "Oh, that's an opcode for sure." You only interpret it as an opcode if your instruction pointer is pointing at it. Um, yeah, but what am I doing? I am I'm adding granularity to my model. So I want to be able to model an instruction. So I have opcodes, I have my state, but I want to actually be able to model the assembly itself because we're going to write a disassembler and do other things, all the motivation I mentioned earlier. But yeah, I want to make like model an instruction here. Like here is an instruction with two parameters, right? It takes an opcode and two arguments. And an argument could be an actual B or a reference to a B, where a B is a lit or an address or whatever type that happens to be. But in this system, our types are only lit or address. Hmm. Oh, Sparkly Dark Matter, you're working on it. You're very close to running Synacor VM for the first time. That's exciting. I felt really close for the first couple of hours, and then it ended up taking another hour. Or another couple hours. I don't know. I lose track of time. I think we're making a worthwhile uh, modeling update here. I hope so. Okay, so let's look at what our type errors are, fix things around. Reg is not a member of A. Right, because what was A formerly? V is an A. For that, V needs to be at least a U15. So we say this just subtype of U15. Not even word, right? Just U15. Okay, so that has that. And I suppose for regrep is the same thing. U15. Um, yeah. And I suppose we can add that constraint here too. So an arg is of a U15. Okay, makes sense. Now constant. We found a constant.v, which is an A. We required a word in order to do the cast. Constant.v, we should know. So v is an A, right? Which is a subtype of U15 that's bounded. Must we say here that show const? I don't like that we need to say that this is a U15 here, because we should just know that by virtue of const only being able to construct U15s. We could go back to having this be a U15, right? That can return a U15. And we don't need to say this here. Um, yeah, we shouldn't have to add that constraint. V is a U15. Um, but no, this could actually be a literal or something like that, couldn't it? We need to be able to distinguish between. So when we're showing a const, we do that generic in A. So we need to be able to know that this is a const of a lit if we're going to cast and show a lit. So I lied. This must be an A. Yeah, I suppose in this case then, when we do this show const, we do add that constraint, but I feel like I should be able. I should be able to figure that out. otherwise. So I might have to do some magic there with the type parameters. So constant.v is a word. Good. Show regref. This is a U15. So given an A, that's subtype of that. A regref is type A. Not found type. This is arg.regref. Yeah, memory can be either code or memory or both, which means a Synacor VM could totally be writing code to memory and then executing that. Maybe the whole thing's like maybe there's a quine in there or something. Fun. Oh, I know the feeling. Totally forgotten how to code, so your day is just reading. That's happened to me plenty. I've forgotten how to code in types. This is good for me. This is a good exercise. Um, I partially forgotten because I don't do it often in Scala 3, and syntax changed a little. So when I'm using and givens here, I know conceptually what I want to do, but I'm not using this on the daily. It'd be pretty fun. Yeah, I definitely wouldn't put that kind of stuff past Eric. V is not a member of argref. No, it is not. Uh, oh wait, we have to extract value. So we have to use registers. So when we show a regref, we need registers. Hmm. I'm tempted just to do registers here as another contextual. It doesn't make as much sense as the other two. I'm going to do that for now. No, I'm not going to do that. I'll make it a proper parameter. So show a regref. We need registers. And then we'll make a nice mechanism and wrapper for all of this later. So val dereft. Well, let's see, what do? We do regref.deref using said registers. And then we can cast that. We can cast that specifically to A, whatever our A is, because we have a cast instance for that. So val v type A. I guess we could just say A. So now we show A here recursively. So we take the regref.name and then we show A inside of that. Okay. That is that's working. And I'm gonna turn these eventually here into like implicit defs. But first let's fix all the other type errors. So from word, we need to have a cast. Right, when we're getting an arg from a word, we have to be able to construct an arg of A. And to do that, if w fits u15, then const w.u15 is no longer w.u15. It's going to be cast w. And again, here on the right side, you can see that in the case of a lit, it's going to be, oh, where is that? Where's our cast instance? Yeah, it's just going to be w.lit or w.address. That's what this cast is doing. But we're doing it generically here. Um, and then we do regref with the reference. This is fine. We can just call regref. What's the issue here? Regref of A, we required arg A squared. Wait, what? A regref of A should also be an arg of A. So we don't need to do any casting here. Let's see what's wrong with this first. Ambiguous given instances, both given cast lit and given cast address match the same type, right? Because they erased the same thing. Given cast lit, given cast address. Oh, that is unfortunate. How do we work around that? I don't think I've worked myself into a corner. There's always a way out of this. Liquid Quake, hello, welcome. It's going all right. Today is kind of a bonus stream where I'm trying out formalizing my assembly. So I'm parsing instructions into an actual representation. I'm not familiar with Fossil. Cool, cool. Yeah, I'd love to see. I'd love to see that when it's public. I think we'd all like to see it. Okay, so this is ambiguous. Match type Synacor cast A of a context parameter of method cast. I think just means we might have to do this at a higher level. From word to arg of A. And then we need a cast for A. Yeah, depending on what that type A is, we cast it differently. But it thinks these clash because truthfully, they do have the same type because these are opaque types. So opaque types aren't as much of a panacea as I'd hoped. The context parameter method cast and package Synacor. Maybe there's something else wrong here. A cast. Well, let's look at how this is used. So we have from word, and that gives us an arg. And what we've done here is we've added type parameters to arg so that we could say what kind of an arg it is. And I think we're realizing that because there's not a difference at runtime between an arg int, between an arg lit and an arg address, we can't take advantage of that. Which means at the level of VM state over here, we couldn't even say as lit. So A is an arg, or yeah, A is an arg of type word. I think we then just need to have three cases here. So if we go back to our instruction, the other way we could do this, so we can do it generic. But we could do lit const or const lit and a const address. So this extends like an arg lit, an arg address, but we'd have to use the same thing for regref. Address constant. So we could say like address ref and lit ref. So this is address and this is lit. Oh, this is backwards. And then now we don't need these types inside here as a parameter. So you don't have to do that parameterized, and we have to type more. But at least now this layer here gives us distinct types. A constant address is a distinct type from a constant lit, whereas an address was not exactly distinct from a lit necessarily. Okay, and then now we just end up having to match on more cases, I suppose. I'd like to, let's go back to our VM state and see how that's actually used, because over here in arg, okay, and arg is of a type A. I was hoping that we could use an inferred type here of lit or address, and maybe that's still the case, because inferred type of lit, these could both we could have like an arg lit and an arg address. They're both subtypes of an arg A, right? Then you still end up having the problem where arg A of a lit or an address are identical. So I think maybe this arg doesn't have that parameter at all. Yeah, that's the whole point of this. We need to remove this type parameter. So these are all like, you don't need to pass anything along anymore. So an arg is one of these four things. And this redundancy here, can we actually, if we look at where it's used, instruction. So instruction one here, we know that this is a lit. So we could do something like a.lit. This argument is a lit. Oh, that's actually already something we sort of have here. So dot value, right? This is a dot value method. And this is working def value, right? This either dereferences it if it's a register, and then it calls dot lit on it. Right. This is all code that we wrote while arg was still generic. And this still works. But now what I'm going to do is I'm going to do arg dot lit. So arg dot value gets the lit value, the potential lit value. But here in an instruction, what I want to say is that this is either so a dot lit, that's going to be either a lit ref or a constant lit. And we already know how to show a lit ref or a constant lit. And we show those different from other things, right? We need to know that it's a lit ref and not just any ref because how the ref is shown depends on what it is a ref of. Okay. And then this is some sort of casting stage, right? So this should fail. I guess it shouldn't fail. It just we're asserting what that is being saved as. So we could have something like this: lit arg is either a lit ref or a constant lit. Whoops, lit ref or a constant lit. I should change those around. Address constant or an address lit. In fact, I'm going to call those vowels. Address val or lit val. There, it's all three letters. So a lit arg is either a lit ref or a lit val. Right, and def lit gives us a lit arg. So our from word method then needs to give us either, well, our from word method until it has the type information. So we can't just do a generic arg. So down here, A, that can't be a generic arg. We could have, or like B here. So we might need to have something like B lit. B lit. Dot value. And that's where we like dereferenced it. Yeah, I think so. This is quite a rabbit hole. I hope it's enjoyable though. Let me see what you're up to before I take a quick break. Oh, what did I miss? El Coulonc did. El Coulonc made a puzzle. Ooh, okay, I have to catch up. I have to catch up with that. But let me go to the bathroom first. I'm interested in this. Okay, so let's take a little digression and look at the puzzles here. Okay, so Zuno got along around to solving liquid cakes colon how's it pronounced? Coulonc El Coulonc puzzle with all the runes. He saw that and ran for the hills. Fair enough. um, has bonus properties, and you've got the link. So let me click that link. It's Coulonc that needs a Twitch login. Oh, wait, hold on. Was someone showing that to me earlier? Yes, okay. I remember this. I remember this. It was mentioned before. Um, it needs a Twitch login. Okay, so I'm gonna do this in my Amazon container. And let me just make sure I don't like show any login details here. Oh, great. Yeah, it shows your password right on screen. Lovely. That was a good instinct, I suppose. And we're going to save that. Okay. Ah, holy shit. Sigil. Oh my god, this is a puzzle. This is a proper puzzle. You're in charge of the Equinox ritual. You've set up shop at the top of the second tallest hill in the parish, and the clock will strike midnight in 3 hours and 33 minutes. You don't have much time, so you'll have to improvise the ritual as best as you can. Okay, you have 3 hours and 33 minutes. So I could do this sometime and give myself that time limit and see how we do. And then is this, so that's elco longs, but then you had your link. So here's the liquid cake. So this liquid cake, this is your puzzle. Permission to see someone. Wait. Give me a second here. My chroma display is set wrong. I wasn't showing any of that, was I? Can I dark mode this? Let me dark mode that. Sorry for burning your eyes. The sudden white text. So you have to meet Santa Claus. Somehow your route became distracted, sniped by some kind of arcane puzzle. Of course, you can't ever get to Santa Claus without puzzles along the way. So there's a grid. Each letter starts with a sequence of digits, which wraps around the edges and stops before the next letter. We have some facts about that. So this is a constraint puzzle. Okay, I see. Is this a puzzle for which you expect us not to use a constraint solver? I mean, it might be small enough to like just brute force the constraints in there, but fun. All right, so saving these for later. Now, where were you here? We're going down this rabbit hole. I think even if we delete it, it counts as progress because it gives us better understanding. Um, but we want at least the other kind of progress where we actually have more constraints in our system. And then eventually we'll make the other kind of progress, which is actually doing the puzzle. But like, we can take our time getting there. This is fun in itself. Okay, so as reasoning through this, and here an arg, we don't necessarily know. If we parse an arg, we don't necessarily know whether that arg is going to be these two cases here, a lit arg, or is you don't know if it's going to be a lit ref or a lit val. So we can't construct this value here at def a arg unless we know the type. So from word, we tried to get around this by saying from word of a type A that's castable. We now just need to say from word lit or from word address. And those have to be two separate functions, right? So what I was going to try and do is like from word lit in the types there, but now I guess it has to be like lit in the name there. And then I guess that gives us the lit arg. And then at that point, is there value in doing this? What are we saving? I still essentially want to type b.value. And if b is an arg that hasn't been determined yet, it is essentially still just a word. Or, we know that's a U15. we can know this much for sure. We can know that it's either a U15 or a reg reference. And that takes us back to this model here, right? We know that's a U15. Of course, we'd be removing this type parameter. Yeah, I think we have to remove the type parameter on args. This in itself might still be valuable. But this show here, so let me just comment this stuff out because we're not going to use that right now. So the type error we were dealing with was that, oh, where'd it go? Ambiguous instances, right? So from word. This has to remain a generic A. We can't cast it yet, which means we can't even construct it. Can't even say U15. I guess we could just do const w.u15. We could still do that. That's what it was before. But now we can't say it's an arg. It's an arg of unknown type. Right, it still has that type parameter. And we don't know that U15 is... Yeah, firmware can't have a type parameter because the type parameter we use is all going to erase that same type. Which means we can't have a type parameter for that. I suppose regref could do that. But what's the point of that having a type? I think we just need to be able to like dot. We can already dot value on it, right? That was still already progress. Right, an arg itself can do that. And I think making these show instances was it's not useful all the way down. So it wasn't useful at the level of lit. We need to like pass that down and say what we're converting with. I guess we could still say using that. And we have a structure that works. It's just that the compiler can't choose one or the other because these two erase the same type. So we can just pass around one of those explicitly. Right? Can we do, let's see if I can write this line of code. So val v equals summon. Can we summon a show of lit? Can we at least do that? That's not going to be ambiguous, right? And it's going to be a show of lit. So we can do that. We just can't do it for a generic. So those show instances are still useful. I'm gonna leave that commented in case we like that idea. But we can remove these type parameters. These only operate on U15. This should fail, yeah, sure. And show const. That should fail. It should also be, no, it's not dead code. Okay. So we need a cast and we need a show in order to do this. And so to show a const, well, I mean, that does compile. We can show const, we can show a register reference. And now from word should be happy again. Yeah, we can show a register reference as long as we pass along this explicitly. I'm not sure if we're running into the same trap or not. The puzzles are about prestige, indeed. Okay, so do we still need this? Okay, so let's get ourselves back into like a compiling state. Arg does not take parameters, so inst. Oh, wait. We do kind of want arg to have type parameters. Right, because we can't show an instruction unless we say explicitly how that is. So unless we say the types here, we can't instantiate that. Well, the only thing that fails here is this from word when you give it a type parameter. So if we instead said lit arg from word, let's try that. Okay, a little bit more undoing. Yeah, the types are back in. Okay. So arg dot from word lit. This is the thing here that won't play nicely. We just say this is explicitly an arg of lit. And then when we cast, I guess we have to, this whole thing needs to have instances will cast for W, or no, not for W. For lit. So using cast for lit. Otherwise, we have a register reference, not found type A. Oh yeah, just a register reference of a lit, and then cast that to a lit because a lit is what's expected. Okay. And now all of this becomes unhappy. So instead of this code here, we're going to need to have like specialized code for our two different cases. So our stack extension A, if this is an arg of lit, then has a method called value. I still like that approach there. But if we're gonna have type parameters here, we need to do this. So an arg of lit, A match reg reference, dereference that, and then I suppose we would need a given. So using cast of lit, right? Or we can actually literally just say dot lit. And now V should be a lit, so we can just say V. We don't need to do any casting here. So we dereference that cast explicitly. Missing type parameter. It doesn't need a type parameter, but we know it's a lit. And then now this is an arg of address. Okay, so an arg of address, similarly, we can just do dot address, and here we can just do dot v. But now that breaks our code below because address can only be called an arg of address. But we want to, so this will have implications because we want to be able to get an instruction. I think what we might end up having where this is nudging us is that something like this set here, or I don't know, let's go back to our easy example, this add. This is going to give us an instruction that needs to be interpreted. So it's going to be like an instruction that's add. And then we say here a dot lit arg. Yeah, so there's a lit arg. No, there's a register. And that register doesn't need a type actually. A register reference doesn't necessarily, in fact, it needs to be on type because you need to be able to save anything to that. So there's still the to reg method, right? So a.to reg. But that is still a reg reference. So reg ref. A.reg ref b dot value arg, lit arg, and then c dot lit arg. So we would have something like that instruction. And now this instruction is something that can have a show method. And it can have a show method because we have the types of all of these. So if we have the type of each of these parameters, then we can summon the show instance for that type and say, okay, this is how we show a register reference. This is how we show something that's a lit or maybe a register referring to a lit. So the difference between this and what I was hoping we could do was that I was kind of hoping I could just do this with like inferred types. Right? Like I was hoping I could say inst and was a type of A. I guess a type of A in this case. If you go look at our instructions here, A is an arg, but it is actually a reg reference. Reg reference for sure. And a reg reference doesn't need a type here. And then arg lit and arg lit. I suppose we could still do it that way. But there still needs to be, I think there still needs to be a method call. Right, because lit arg. It's the place earlier where we were basically def value. Yeah. And then, so when we're parsing the instructions, we'd parse like these instruction bits here, right? Now we can take these instructions, we can extract them into something else. We can do show, right? We have a value representing the thing that we want to do. But now we need to have like a way to run that. So like to run an add instruction. And then we would say, well, let's see. We have val I equals that, right? And to implement this, then we do something like this.store I dot a, which we know is going to be a register, right? And then I dot b plus I dot c, I dot b dot value plus I dot c dot value. Yeah, that might be like a method inside of instruction. So we'll comment that out as like an idea. And here in instruction, what would that look like? We'd have, I don't know, maybe inst3 here has a method. Or you know what, let's do it at the most generic level at inst. So there might be a method here, and def tick. And then, we have our state. Or, let's call it VM. And this gives us another, well, this gives us the tick from earlier. And then we do op match, right? And then we have case add. This is the op of this instruction. And then this has a B and a C. So case add, then we do bm.store, and then A, which at this level for the instruction, I don't think we have the types, or like we have to match on them. Right, even if we were to put this inside of inst3 over here. So we have A, B, and C available. In order to call a store, we need to get a lit here. So we don't already know that B is a lit. So this case here only works, which makes me think that maybe we have to have like an add instruction if we're saving this. Yeah, I guess we do have to do like an interpretation. So like we were doing earlier, b dot value, meaning lit, and then plus c dot value, and then your a dot to reg, the same kind of thing. Yeah, we can't do anything fancier. So we have the same thing there. We just have three arguments, A, B, and C. So when we show an instruction, we need a lot of guidance there. So if all that type information is in there, yeah, if we can create the instruction, then we will have the type information. It's just that we have to match at runtime. Because we don't have at compile time what those are. Right, like instruction has parameters, and at this stage there's gonna be like question marks. So so we can't know here. We do still have to give it guidance. This is something I'll have to really ponder on. I feel like it's possible. I just don't have the type level chops. I haven't like convinced myself that it is impossible. So we can't have a generic show instruction. I think is the unfortunate reality here. Um, okay. Well, I'm gonna at least I'm gonna save this as a stash because I still like the idea. Um, everything we've done here, not everything. Not everything, just part of it. So I'm not gonna stash it, but I'm gonna save it on my stack of stashes. So in main, there's some stuff in VM state, and then we can unstage it afterwards. Oh, what's this thing here? Registers return into U15. Anyway, stage that. Stage instruction. I don't think we need to stage anything else. Z, we're just gonna save. Yeah, I think we just want to save the index. Okay, cool. Now we can unstage that. And let's make the code we actually want. Hmm. So from here, we're just gonna take a step back to where we were earlier. I think it's worth a shot. I'll keep thinking about that, and if I do figure that out, I think it might be worth sharing. Um, but yeah, we're backtracking all the way on this. I think it was still worthwhile that we got this arg. Alex NK Dev, good morning. Oh, I didn't realize you were across the Atlantic. Or holy shit. Um, or it's just 4 a.m. Are you stateside or over in Europe somewhere? Yeah, just in time. We're winding back a little digression. So Kant still needs a type parameter, right? It's U15. What's this diff here? How do I show that? Yeah, well, we're not using type parameters. So this is what before. V is just some U15. And now we don't need to extend in either of these cases, do we? Okay, non-generic, making things non-generic. Constants are always just U15. And then we have to give runtime guidance of what to interpret those as rather than compile time. Regref. See, this is a case where a regular expression find and replace would be nice. We don't need from word lit. These were nice ideas. I'll just leave commented in there. I think we can go back to the idea of a case class instruction with its arguments. So A, arg, B, so a list of args. It might be the case that a number of args is still valuable. I know. We'll leave the idea there anyway. Inst and args, list of arg. And there's an inst 0. Am I East Coast? Yes, I am. I'm East Coast. Hmm. New York. So you're either up really early or it's closing time at the bars and you just got home. I lived in New York City until the pandemic hit. I was in Brooklyn. I think I mentioned this. I was organizing a conference and the pandemic hit and I burned out. Let's see. A place with nothing. Um, you're trying to do AOC 2016 in Scala. Oh, interesting. I will be very curious to see the results afterwards. I'm wondering, have I done any 2016 day worksheet? I've done a handful of them. Oh, no, no, no. I've only done 2 from 2016. I don't know why it shows those 2 in particular. They were probably referenced by later advent of code problems, so I went back to catch what the reference was. Okay. This should at least help us carry the values across. And then as for how we print them, it will depend on the opcode. Yeah, I think that is fine. Let's go back to VM state here. We are back to doing this, which, no, I'm fine with. That was actually, it was nice. And instruction. Only different code for that altogether. The show method, though, the show methods. We'll have something similar. Okay. And what else would be break? ToReg is not a member of Synacor numbers.word. Oh, right, because we're passing a word there now. All of those show functions are, show helpers are broken. We need to implement new stuff here. Because we're not passing around words anymore. We're passing around args. So the fact that we're using args instead of raw words is at least an improvement, even if we're not able to get a type parameter in there. This is fine. Okay. What else is broken here? Let's comment these out. It's double definition. There is another definition to show somewhere. Oh, yeah. We can delete that. You're wondering what .view does. Oh, I can tell you real quickly. So a view works on any kind of collection, right? 324.view. And this is kind of like an iterator. So an iterator lets you go through everything at one at a time. So let's say you're doing a map. So +1. So if you have an iterator, then you're looking at 3 plus 1, 2 plus 1, 4 plus 1, etc. And then this end result here is also an iterator of int. So what that avoids is making a whole collection, right? Otherwise, this would be constructing a whole new list of 4, 5, 6. So that saves on memory in some cases. It can save on execution time if you only end up doing like a .next call on the iterator and not consuming anything. And a view is basically like an iterator, but you can use it multiple times. So a view just avoids making intermediate instructions. And if you're to do like .map and then like .filter and I don't know various other combinators, the execution order is first 3 gets mapped and then filtered, etc. And then 4 gets mapped and then filtered and etc. Right? Rather than what would normally happen in a list is we get a whole list first of everything incremented, and then we do a filter on all of the elements. So this is like a virtual, like, well, it's a view into the collection. And that works for list. If this was a vector, right, and you were like indexing into that, so, let's say I'm just taking the 10th element. If I'm taking just the 10th element, then it won't compute +1 for all the other elements. It'll just take the 10th element and do the compute there. Yeah, it's nice. It's handy sometimes. Yeah, happy to share. So an instruction, we're still gonna do instruction dot show, I think. Or at the very least, let's convert this. So we're not gonna do an instruction yet. Okay, instead of show lit or an a arg, I mean, I suppose it could still be show lit. Yeah, and in this case, it's a lit arg. And then we do lit arg match exhaustive here. If it's a reg reference, then we do like our show reg reference. I think we did an implementation actually somewhere already. Let's see. There should be a show reg reference. We do still need this. So show reg reference, given that reg reference itself. Rep, pass along our registers. And then, yeah, that's it. And this thing, I'd kind of like to be able to wire a little bit more. I think we need a method called show arg. Yeah, so show lit arg. I guess we're implementing that here. And if it's a regref, then we do that. I guess we could do. Let's implement a show arg. Stiff show arg. And then it needs a show reg, a show of reg reference. And a show of constant. And this is a method definition. I think what we actually want is to give a type class instance here. So we'll put this inside of arg. Let's finish off this definition here. So it's going to be a arg, a match. So if it's a reg reference, ref at there, val at or const there, then we do show reg reference of reference and pass along registers. So we need registers. I'm going to try making this a registers in implicit context there, a context parameter. We don't call them implicit anymore. That's a dirty word. Otherwise, show const. Why does this have a type parameter? Because show arg, right, we're back to the show arg can't actually be generic. It has to be show like lit arg. So arg can't have a show instance. So in our object then, object arg, we're gonna have a function called like show lit. Or that's not even gonna be in the object. It's just gonna be a method here on arg. So we show it as if it's a lit, and to do that, this show const needs lit as a parameter, and we pass along that const. Regs. I am Dev Alex. Thank you for follow, and Kanya Dav. Welcome to the channel. Okay. So in a minute, we should be able to, in 5 minutes, maybe 10 minutes, we should be able to show any argument either as a lit or an address. So we pass the registers along here. Oh, how do we give that a name? The others aren't. Oh, no, using. Um, so some context parameters can have, like you can give them all a name or you can give none of them a name. I know that. But can you mix them up? I guess I could do multiple parameter lists. So using registers, just call them regis. How does that work? And show regref has ambiguous. Right. We can just do given cast lit. I wonder if we can do that with types. So given or like using cast of lit, and we're just passing that along explicitly and saying which one do you want. Okay. I suppose show regref we can just give a lit here. Show regref as a lit. And we don't need to say using cast lit because that will be inferred. Okay, that's better. So we have show lit and we have dot show address. Address. So we call show regref with address and show const with address. I think it might actually be the case that things work out here. I'm feeling like this can actually work more generically than I thought. And whatever I was stumbling into earlier, I was just doing something a little silly. Okay. So that works at least as static methods there. We have, so let's go back here. We don't need type parameters there anymore. Ambiguous given instances over here. Yes, we're not going to do that. So we don't need a show lit method anymore. So when you show a push, we have the show args method. No, we have a.show lit arg, where like a is an arg, right? Yeah, and then it has a method called show lit arg should dot show. No. Yeah, an arg has a method called show lit. What is A? A is an arg. And an arg has a showlit method unless that's failing to compile there somewhere. I think it's just not seeing it because this is not compiling right now. Let's give it a shot to compile here. and look at what else is going on here. Overriding, okay, yeah, instruction does have its own compiler errors. Overriding val, okay. So this needs override val p. I suppose we don't need to extend and pass along that parameter. Let's try that. And then it becomes overriding nothing. One sec. How about that? Okay, yeah, there we go. Given cast. It's impossible since def cast. Oh, what happened here? Method cast has different signature than the overridden declaration. Object creation is impossible since def cast from word to A. Yeah, it should be from word to A. We have a def cast from word to A. A and trait cast in package Synacor is not defined. We weren't seeing this error earlier, so I'm not. Class implements a member with different type. Override def cast. Which returns a lit, whereas it should return an A, which it is returning an A. An A is a lit. Oh wait, I see. There's a type parameter missing here. Which actually begs the question here: why would it need? I don't think it needs a type parameter. Okay, there we go. That's all that happened. I typed a sporadic parameter. Okay, and for show address here, what's going on? Parameter A in def show does not match parameter lit. Okay, show lit. Oh, this should be address. There we go. Okay, show const, we have that. Show regref, we have that. And these two are both written generically. Right, so that works on either lits or addresses. Which makes me want to create given instances for them. So given a show of a const And my given needs, I guess it needs a type parameter. So a given def. Let me just look up the syntax here. If we want to give it, okay, so we do want an anonymous given, and this is the new syntax. This colon, you can just do it with a colon. It looked awkward before with a weird, as like an experimental stage, I guess. And given a t, what is this? This is a given function. So given that you have that, an ordering for t, give us an ordering for a list of t. Okay, yeah. So then in this case here, for show const, I suppose I think we want a context function. I think we could give it a name. Okay, so this is just defining an int ord, right? So that's not parameterized at all. This is relying on a different ordering that only works if we have an ordering of t, because we're recursively defining the ordering of a list based on the ordering of the individual elements of a list. So that'd be like how you sort strings, given that you know how to sort letters of an alphabet, right? And I guess I could do an alias given. Okay. So if our given relies on other things, given it can be anonymous. Um, we have an A that has a show and a const, right? And a cast. And then that goes to a show or a constant. And actually, are we even using? Yeah, we're using that. With a method called show. So we have to implement a method called show, like this here. I think maybe I should just update my Scala version, make myself happy here. I should have done that at the beginning of the season, actually. Um, and I wonder if I could actually just take this. And this is the name of a function that gives us um, oh, you know what? Actually, so we had the show const. This already has this is the structure of show, right? We're showing a const here. This method. Um, so let's write the method that gives us a show instance. We'll do it that way. I think got it now. So def, let's do this. And what this gives us is a show of const. And a show of const is going to be, we'll just make an inline definition here. And this show const is our just show implementation. So def show. No, this isn't a new const, sorry. This is a new show. And then like we override def show. This show has a type parameter though. I think I need to put my type parameter somewhere higher level. We'll put on to foo. There we go. And then we have our outer context. This should be referring to the show from down here. I'm just gonna rename that real quick so I can use it, and then we can fix that later. I just want to test this here, that this thing works like I hope it would. Okay, method show has a different signature than the overridden definition. Yes, it has a different signature because these parameters need to be elsewhere. So we'll move that up into here. Okay, great. So this is a show. And val given, and this can be, we can implement this as like an alias given. So given show const then equals foo. I guess it needs a type parameter, right? Or we don't have val. Ooh, that depends. I guess this is an A to a const. A const for an A. I don't think I can do this. So like we need a cast and a show for A in order to show a const. So this here is actually going to be something like, if we were to give this a name, it'd be show lit const, right? Or no. This can be generic because show lit const is just show const with lit as a parameter, right? So show const, can there be a parameter here? And then foo gets that a. No given instance of, wait, what? Cast a for parameter x1 method foo, right? Because I guess this needs those same parameters. Cast and show. So A has a cast and a show. Okay. Cool. So I think I actually can just take this thing and make that a given. Okay, yeah. That's a given function right there. This gives us a show of const. And this is where we put that colon. But now we're just going to say with, and then the definition, the trait body, the implementation body. Okay, cool. And this can be anonymous. So there's that. Okay. I think the syntax they're using here is a context function. Let's look at the whole book here. Some contextual abstractions. We have context bounds. We have multiple context bounds. Deferred givens. No. Context functions are functions with only context parameters. Their types are they are context function types. Okay, use this question mark arrow to say that something's a context function. So an execution context must exist in the context somewhere, and that's how you get an executable. So this here is actually a context function because it only has these context parameters. So how do you write that? Ensuring, I don't know. We have something that does work here. So I'm gonna run with that. Okay, so we have a show for a const, given that we have some U15 type. That's great. That is a generic. So we can have something similar for a regref. We'll make this a given. And this gives us a show of a regref with override def show regref. Oh, but this here, it can't be a given function. Well, it needs registers. So I suppose if we put registers in the context as well. So we have override def show. Regref is a parameter there. Gives us a string. And as the show any, or rather this implementation here. Okay, that A is up there. Okay, so let's make this a thing that returns show reg. And this equals a show of regref with this definition body. Um, okay. So that works there. And I think maybe we can just do the same kind of translation. Right, that's a given. But it can't have. Hmm. Okay, we could have multiple parameter lists. So given that we have registers in scope, yeah, we can do that. Okay. And this can also be anonymous. Okay. Now, we don't need separate show address and show lits. We can just have given. So we have a type A as E15, and also has context bounds, cast and show. Is that the right syntax there? And given that, get a show of arg with this implementation. So override def show arg is going to be our show any function. Or no, we're going to match. So arg match. And we're going to do this thing here. But now this thing here isn't the thing we really should have to write, right? Here's what we know. we know that we can derive a show for any const, and we know that we can derive a show for any register reference. And we also know that an arg is just a const or a register reference. So given that we know all of those things, we shouldn't have to write this code. This is something that the compiler can figure out on its own. We are writing it explicitly, but this is the basics of what I mean by derivation. Is this even compiling here? No best instance was given for that. What happened here? That was compiling. Oh yeah, I think it's because I have this in scope. Yeah, that should be compiling right now. What's going on here? This A. A needs to be a regref. Oh, right, this is the show any. Or, this could actually be a show A.show. Show A. That show. Yeah, that way you don't have to say show any. Okay, we're almost there. But I do need to go to the bathroom again. Be right back. All right. Let's look at derivation. Because there's new tools in Scala 3 that I haven't used yet here. Contextual abstractions, type class derivation. Okay. So type class derivation, a way to automatically generate given instances for type classes which satisfy some simple conditions. So a type class in this sense is any trait or class with a single type parameter determining the type being operated on. And yes. So here we have a tree. and it derives equal ordering and show. So in this case, as long as we have givens for the things that it relies on the t, the derives clause generates the following given instances. So it'll give us a given from t with equal to equal of a tree. So given that we have an equal for the t, yes. Okay, but derivation only works for things with a type parameter. And the type parameter we were adding couldn't be an opaque type, unfortunately. Maybe it can. I was just doing something silly earlier. Okay, well, let's try. I'm gonna try this real quick and see if we can make this completely generic. So there's show address, there's show lit. Um, so it's gonna have a type parameter a of that's some U15. And this is using a show regref and a show const, but not just any. Here's the problem. There are two nice ways to get that, and they're both functions that depend on the A. Like, can this here at least be a thing? Like, this compiles. Oh, no, because we haven't actually changed that. So let's say, that was a show regref and show const, which are both generic. Okay. The problem here, no given instance for type cast A was found. Right. Show arg for type A needs show arg for. I'm left to wonder if I can't actually derive it. Why couldn't I derive it earlier? Because there were two different ways to. There were two different good right, show lit. Like these were clashing. So my show lit was clashing with my show address, but maybe it was just because that place was underspecified. Right, maybe the place I was trying to use it. Let's okay, def foo there's some A type U15 using and then we're gonna have that A, which is of type A, and then using show of A, right? Does this work? Show A dot show A. And can we do that on foo? Let's see, word dot run int 1234 dot to lit, or rather just not lit. let's see, that far. We can't have a top level expression there. I mean, that compiles. That compiles just fine. Right? Like this is important to be a lit. But if we were to say like address here, surely that'd fail. Yeah, that fails in that case. Wait, can we actually add the parameters? I think we can, in which case we can just use derivation. What did I miss? Okay. Well then, let's say that this derives so we have an A that's type U15. And let's use that derivation here. So we just say well, let's make sure we understand what we can do here. The derives class generates the following given instances in the commanding object of T. So there's like show.derived or that. Is discouraged to directly refer to the derived member if you can use derives classes instead. Yeah. Exact mechanism. Okay. So let's have our arg there derives show. And for that, we need to define a derived for show. So the exact mechanism, we can gloss over that. So show needs a derives. This compiled derives show. Value derived is not a member of object Synacor that show. Implementing derived with mirror. Okay. As seen before, the signature and implementation of the derived method are arbitrary, but we expect it to typically be of the following form. I think maybe it'll be instructive to do this manually first. So we'll wire this together manually, kind of like we were trying earlier, and then show what derives gets us afterwards. That'll be a good exercise for me. So there's a type parameter there now. And I suppose these also have type parameters. A, that's a U15, extends arg. A, let's just try that. And now here, using show regress of A and show constant type A, where A is a U15. And what is our goal? Let's get something more like this. So that needs to be const A. This needs to be a regref A. And then this code here earlier, show arg In that case, we can summon show regref of a. Otherwise, we summon show of const of a. And this gives us a show of arg of a. And now give an instance of Synacor cast A with found for parameter x3. Right. We have other type errors to fix before that. Should just be here. Oh, I guess we need to use show of A. Oh wait, what am I even doing with this? I don't need this. I want this. Reg. Yeah. And we have an issue here. No given instance of the show of arg that reg of A was found. We need registers. So using, yeah, we can't show it without registers. We found that we required a string. Oh, we summon that show, and then we do show on ref. Dot show on const. Okay, cool. That is fully derived. We just need to fix compiler errors elsewhere. These we don't need right at the moment. Extension on a regref. An arbitrary type. And from word. We can just say that that's U15. Fine by me. Now we go back to having types here in all these args. So arg, and actually we're missing. These need to be distinct type parameters. And one more type error here. And we don't need these right now, do we? I'm gonna keep those ideas because we might have to backtrack a little bit, but this is promising. I'm sure I'm doing more work than I need to. We'll call that show lit arg and show address arg. we were able to replace that with just show arg in general. Right, so this is like our show arg. Okay. Well, let's see what else. Still needs to compile. Argument A does not conform to upper bounds. You're right. All of these need to be U15. U15 and U15. Okay, that fixes that. And now that compiles. Now I just fix these args here. Add some type parameters. They should be inferred everywhere, so that should be mixing after that. So arg given a type parameter. Oh, no. Given a type parameter here, A. Then you pass those along as arguments. And what are the implications of that? And package Synacor does not take type parameters. I mean, it does. We just changed that. Oh wait, object arg. Sorry. It does not. This is a companion object of our type. Okay, and from word, I think this. Oh, I guess these can be args of U15 because we can't pass along. This is where it fails. From word is and does not take. Wait, it does not take type parameters. Really? Right. Yes, it doesn't. Arg U15 required some A, right. So we can just say these are all U15 for now. So this is an from word gives us an arg of U15, sure. And we required, we're getting a different U15 for whatever reason. Oh my god. It is 5:12 a.m. I can't believe I am either. I think part of why I'm going in so many circles is I'm so tired. I keep feeling like I'm almost there. So I think I'll chase it for another half hour or so and see if we get there. And we'll call it a win if we end up replacing all of our two-string code with this, where we're using our actual structure. But yeah, good night, Zuno. Thanks for sticking around. So arg.from word here always returns an arg-u15. And it doesn't like this type, where u15 is a type in the top level definition package with bounds under word, and u15 is a type, is a method, is a type in method A. From word, we tried to show that Synacor numbers.u15 conforms to none of the types shown below succeed. Well, what's this u15? Oh, wait. U15 was a parameter here. Silly. Okay. Yeah, there we go. So that goes back to compiling state. Here, dot value address can only be called in certain situations. So we have an arg a, and this is the case where it's a lit or not. Yes, another half hour, 3 hours later. But this is our bonus night. We're just adding extra stuff that'll make the challenge easier. Okay, so we take this. I think I will just specialize this. So extension value only works on an A that's an arg of a lit, right? Yeah. And then this extension only works on an A that is an arg of an address. And this deref method, yeah, that gives you 15. This gives address. V is already an address? No. A is an arg. An arg of address, which means that V in there should be. Oh, yeah, I've added a type parameter. I haven't actually added that the V is of that type. So, how'd you spend your weekend? uh, this is my Saturday night. This is what I chose to do instead of dancing. What other type issues do we have? A.address is not a member of Synacor.arg of U15. Oh, right. Yeah, because this A is going to give us a U15. Unless we say, I wonder if we can make that type parameter. We might be back to the square here. So we say that's a U15. If we're just doing the minimal to make it compile, not changing this yet. So these are all args of U15. And this needs a type parameter that is a U15. There we go. Cool. So that should get that compiling. And what's this? Unreachable case. When did that happen? Okay, so we're actually compiling now. Your Saturday night is watching me do this. Fair enough. um, we're almost there. Okay, so we're compiling. We're compiling. And I think the next step, let's just look back at the instructions here. I eventually want to make like all of this derived. All we should need to provide is the instances for lit and address, right? And then all of this shouldn't need to exist. This should all be all of these actually, all of these should be derived. But here I'm explicitly defining the three cases for the enum of like how to get the show for those. Um, I think now we need to change this V. This V should always be a U15, or not. No, no, it should always be an A. So let's change that and get that to compile. Oh, you know what? Let's just verify in the console here that we're able to still run things. Great. That seems, yeah, that seems like that will work. So V is an A. And what does that break? That's breaking nothing so far. I think once we use a more specific type, so let's go to VM state over here. And we will need a replacement for this. So this is assuming we have an arg of U15. I think we need to be able to say like dot lit on an arg lit. Let's start with this. Let's start with this here. Comment that out. And let's look at our definitions of A. Let's make these generic. For that to be generic, I guess we have to make this from word generic. So again, parameter A, yeah, let's go to from word. Okay. A returns an arg A. So from word now needs a cast. So given a cast there, and inside this fits. Well, no, we still do that. We still do the fits, but this const is going to be casting because this const needs to be a const of A, where A is a subtype of U15. And we'll do cast A.cast W there. Okay. That looks there. And now let's go back to VM state and see the fallout from word. From word here. Like that. That should compile. No given instance of typecast A is found for context parameter. Oh, yes. We do need bounds here. Um, and this type parameter we're passing, we do need to say that that is a subtype of U15. Yeah. Type that we're casting to. Or the type of R that we're casting to. Ambiguous given instances. Okay, here we go. Both object given cast lit and given cast address work here. So in A.2 reg, right, because we haven't given it a type. Let's just say that's lit. Okay. Right, so we can't call the method A without a parameter. And since this reg can actually be anything, since this toReg can be, yeah, since all we care about this is the reg, then ideally, like, we should not have to pass a parameter there, but we do. So I'll need an ergonomic workaround for that. Okay. Next one. Every instance of toReg. Right, because we have that A is word. So here B is a B lit value should work. Right? Maybe for now. I'm hoping I can get rid of this later. But for now, I just want reg references. So reg all of these. And it's going to be a reg reference or just maybe a reg rest. It's just the register. Arg.from word given, I know, let's just say U15 dot to reg. Right. Here, no given instance of cast. Right, because we only need the cast. Here's the issue here. Our function from word, this requires a cast only because the const case requires a cast. But we're only using the register case. Okay, for now, let's just say lit, but we gotta fix that. That's not nice to have to hack around like that. Okay, so all the cases where we're doing that A.2 reg, right? We're gonna replace that. So A.2 reg becomes A reg. And similarly, all the b.2reg b.2reg becomes breg. Oh, there were none of those. Okay. Now jump requires an address. Yeah, so here's a case. Well, let's start at the top. Some of these are not needing any help. So this needs help. This is we're getting the value of this. This should be inferred, right? Because a store requires a lit. I think we want a new like value method. So you can call value if that's a lit. But I don't know. So an arg of anything. So some a that's oops, that's U15. And we're going to give an arg of that type A. So we're no longer going to have a separate value and address method. Value is just going to return A, where it's dereferenced. I have a feeling I should already have this defined somewhere. To reg to value. I don't know. There's two const. So def to const. Right. Const A equals this match exhaustive. So in this case, we deref r.deref reg.deref. No, we want the reg ref itself, so the ref there, ref.deref. So in this case, we need registers. Okay. This is to using registers. This deref method, let's summon the registers. Okay. Deref that, and then we need to cast it. So toConst has a parameter with a cast instance. So cast then cast, and this will give us a const of A. Cast of A cast. What's the issue? We found an A, we required a constant. Right, we need to wrap in a constant. Is that what we were hoping to do here? No, we want the value inside of the constant. So this is actually returning an A. Yeah, so value is an appropriate name. Cast a.cast, we dereference, and we get an A. Cool, we found an A. And then now for this constant here, that should just be that V is already an A. So V. So when we deref, we get a U15. Okay. I'd kind of like to add a cast to there. To do use cast. Oh, what's the issue here? Found V of type A required A2. A is a type in a method value with bounds. Where this A that we found is a type in class arg with bounds of 15. Type in a method type, so I shadowed somewhere. Oh, hold up. Yeah, value. We didn't need a type parameter here. But we do need cast of A. Okay, now we don't need this because an arg does just have a value. So anywhere we were saying arg.value, we can now just say be lit.value. So we get an arglet and then call that value. And what's the issue here? No given instance of type registers is found. Yes, so we need to give in registers equals this dot registers just to make all of that compile. Okay. Okay, make that private given registers. There we go. And make this given instances for this a dot value because we don't know what value we are necessarily doing. Yeah, push here. We're doing it with an address or lit. We're doing a U15. Geez, we could just say it's a lit. Can we say it's a U15? And if we do that, I worry that we'd have ambiguous. Yeah, I assume the stack, much like the registers, only take U15 values. No given instance of type Synacor cast is found for context. Parameter of a method A in class VM state. Right. Because we need to implement one down here. So cast U15 dot U15. Found a U15 required an address U15. Yeah. Okay. Required address or lit. So we're gonna go back to push here. And we're gonna change that because It should be on any U15. Dresser lit is already U15. Okay, cool. Now in this case, push requires a U15. I wonder if we couldn't just say, like, shouldn't that be inferred? Maybe if value here weren't a method, we need to change the order of the parameters, basically. So if we have a method, def value of an argument type A, this gives us an A, right? And this would just basically be A dot value. Yeah, using our registers and whatever casts. No given instance of type cast is found for the parameter. Yes, we need a context bound saying that's castable. Okay, great. Now instead of b lit value, I could just say value, and the type should be inferred value of b. There we go. Yeah, that gives us type inference. Value of a. In this case, both objects given cast lit and given cast U15 match that type. I mean, so like we could be specific and say U15 in that case. I guess we have to in that case. Okay, let's look at everything else. Store needs a lit. Okay, b dot value. Let's say, x is going to need to be a lit. If b dot value is equal to c dot value, then one not two lit. Okay, so this comparison here. We want the raw, I guess we want the U15 value, don't we? So B U15 dot value, C U15 dot value. Yeah. I like that this is making it explicit that it is making explicit that we're comparing U15. So like, were we thinking about B as an address and C as lit, that this would still pass because it would upcast them both to U15. Right? It makes it that bit explicit. And I'm starting to see like this whole B dot value as redundant. So A, B, and C, like maybe instead of args, I do still need the args. But we could have, a method, for example. So let's see, def b here. We could have a method bval, b value, and that's going to be some infer type A, that's a U15. And we return that type A. So we do this whole from word And then we just basically call our value method on it from earlier, or r.fromWord to an A. We want this bit here. Yeah, that's what you want to work off of. And dot value. And over here, we need to give A is a type in value and method B value bounds. So we need to cast for A, B value given that that has a cast. Okay. All right. Which means B altogether. I might just like to write B. But I don't know yet. Like B with a type parameter, right? We could explicitly say it where necessary. And then this whole A, B, C. Okay, so A value should be inc1, B value should be inc2, C value should be inc3. So we could also write that. B value, where the cast is inferred. This is a lit. And this is an A value of type U15 in this case, right? A reg, A value. And, I think if we decide that we don't need args, if we don't need to return args, then maybe we'll shorten whichever one is the most useful, the most common case. So we can name this more explicitly for now. So you name A, well, okay, like these are all args. On this, why is input always storing to A? Oh yeah, I guess it just always does store to A. I guess it's an A reg. Yeah. A register. Not found value B, so all these places where B is used. So a B value, and it needs us to give a specific type, U15, equals C value U15. Okay. Def A arg. I have a feeling this is how we want to use this. And we can just say whatever our letter was, we can short it in this definition too. Arg, it's just that arg and then dot value, where, that is all inferred from context. Okay. So dot value becomes redundant here, but we do need to say it's a lit. I think. Wait, where were we? Unitic b dot value can just be b. A of type U15. This is just b U15. C U15. I'm liking this. I'm liking this. So if b U15 is greater than C U15, and we just jump to B, jump to B. We can infer that that's an address, so no need to cast it. Let's see. I think we can do type inference if we do that on the other side. So 0 to lit is not equal to A. Nope. We need lit. Why is it both the lit and 15, but not the address? Okay, so let's say that explicitly as a lit. This 2 lit can be compared with that's any. I see, that's fair. We'll put it back in that order. It's more legible that way. So instead of a dot value, we say a lit. We don't need to say a dot address. Where else? That's not a member of U15. Right, that's only a lit. Arithmetic. Oh, right. These better be U15s. Checking equality. Let's make those U15s. It's already an all-nighter. But hey, look, this is good progress, isn't it? We're not just throwing words around. And we're able to use type inference to our advantage. Okay, so now all of these binary operations. So b dot value plus c dot value, can that be inferred? Let's see. B lit plus c. I guess we have to make that explicit. Okay, all the c dot value, replacing with lit. And b, adding explicit lit there too. This, I'm surprised it can't infer that. Well, I guess, yeah, the order is wrong because this is a method call on that. Can we actually just do? We do that. Oh, okay. No, it can infer it. It's just the parens were getting in the way. Nope. 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 It does need lit. And here we're reading B, which is known to be an address. And when we read, we return a word. We return a word from memory, and then we cast that to a lit. Yeah, it's been a half hour. We're not done, but we've definitely made progress. And look, this is completely inferred. So write requires an address. Now let A, B, we can just say A and B. Bryce910, thank you for the follow. r.fromWord.w.address. What is all of this? From Word, how does from Word work? We can just do that directly to an address. So we don't need to say dot address. We improved that. So we do get the arg, and then we get the value of that arg. So an arg of E15. Why would W ever be an arg, though? I don't think you can pull. Can you pop a register reference itself? Okay, I'm gonna leave this previous line commented. That's kind of surprising to me now that I see that. We jump to an address. We're getting that address from this word. You know what? I think we did realize. Okay, so we'll do something much like this here. From word, and then we call dot value. And it infers the types just fine. Okay, that is still going to be the same behavior. Output A. And what's the argument of A? We need a lit. Oh, yep, that's inferred. Cool. This value method we no longer need. Hey, we are back to compiling. We are back to compiling. Okay. Let's run it. Check that self-test. Yeah, great. All this old stuff we don't need. We're not going to do anything like it. Now we just need to get back to showing everything too. So in the push case, so we have up match, and the push case we're doing, well, it's deleted now, but A as a value, so A reg. No. Push. What was push printing to? Let's look at our spec. Spec push. Okay. A is a literal or a reg, and we push the value onto the stack. I don't think it's actually just a literal or a reg. It could be an address. We don't actually know that though. So I think this then is a case where it's deleted now. We would have been calling show reg. No, not show reg. show args. Right, as opposed to show address. Let's see, show args, a.reg name, yada and yada. What happened to show args? Did we delete a little bit too much? That we want to delete. No, this we definitely don't need. Let's look in here. What did we delete? Okay, we have a show arg. And the original definition here was show args. And show args, does that still exist? Show args. It's certainly called. Hmm. Yeah, I guess show args was doing the printing of the address that the instruction is running at. So let's see, def show up. We'll give a string here, and it's going to be just the first bit. So we show the address of PC. So PC, and we'll show PC. I'm going to rename this to show instruction. Next, rename symbol. Nope, we can't rename that. We'll show the program counter. Or, let's do it more manually because I think our shows an ampersand. We'll say at this address, pc.hex, colon. And then we have the op. I'll show up. It's just gonna be something like this, where we take the op. Okay. And for push, we'll show op plus. Now we need to be able to show a particular arg. And we can do that. A arg of type literal, right? Found unit required. No definition for show. I think we have a show any function. Oh, I guess we're not even compiling, so let's do op match. Here we go. Okay, show any, no given instance of type show arg lit. Okay, we need a show arg lit. I think we'd be able to construct that. So if we go to inst here, show arg lit. this one here will give us a show arg a, right? And that file is compiling. So let's try to summon. I'll just write it here. Def foo equals summon show arg lit or val foo. And for that, we need to have certain things in scope. I guess we need to have a show lit. I mean, that is already in scope. Let's make this a def. So we have an A, it has to have a show. And I think it also has to have a cast. Cast and a show. We're making a skit. A given instance of type Synacor.show is found for parameter x of method summon. Oh, hold on. Let's do it this way. So using show of lit. Let's have a show of lit. And we also need the cast. Yeah, we have all these givens right down here, right? No given instance of type Synacor.show. Arglet. Oh, right. We still can't find it because in order to use that method, okay, let's say we have a cast of it. What else do we need? So let's say our parameter needs to be U15, so we've got a lit. It needs to have a cast, it needs to have a show. I know, let's give this a name. Given show arg a. And let's try to call it. So using show arg a, or rather arg dot show arg a. Second. Is that in the? Oh, hold up. These should be. These should be in the companion method. That's why I kept running to like accidentally having two different A's in scope. Redref.ref. Well, where does dref come from? Object arg. Oh, right. We already had an object arg. Let's move these into the actual object. All right, so we basically just weren't finding these instances because they weren't in the companion object. So they were not in the implicit scope. Okay, so this should work now. Cool. And we should just be able to say show. All right. I think we've got that. Is object more like an OOP class or category theory object? It's more like an OOP class. So an object is an instance, an instantiation of a class. Uh, right, so you can just make an arbitrary object at any time. You could do like a class C and then object B extends C. And that'd be much like doing like val B equals new C. But an object, can have its own methods instead. But most of the time, the reason what you see here are companion objects, and it's just a nice namespace for the static methods that have to deal with arg. So these are all static. So basically, yeah, your companion object is your static namespace, and it's used in implicit search for any context parameters. Okay. But no, it's not like a object in OCaml. Camel uses some names for words differently, like functor um, has a different meaning. I can't remember exactly. So we have show op plus areg.name. I kind of don't mind inlining this. You don't need to have that. So this becomes show args areg.name. Okay, fair enough. Fair enough. I'm just not sure about OCaml. I just know to be careful about the terminology. I mean, OCaml is basically like the ML language that decided, hey, let's try and do some OOP in here. And then Scala's like, yeah, we like that idea. Let's keep doing that. Um, okay, yeah, I much prefer having this whole thing be explicit. So this show up, let's not do that. Um, okay. And we can just keep doing these for all of them. And yeah, there is a little copy paste, but a.reg name, and then a space, and show lit. I don't think we need show lit. I think we can just do literal A. So in this case, A lit. Show lit A, right? Okay. So show args. That's not a thing. We just do reg name. Okay, reasonable. Method apply in class string ops does not take type parameters. Show in class string ops. So this show gives us an should that apply? Oh wait. Let's just show on the A. And A needs to be a lit. And get assert that that's lit either by doing parameter here. Yeah, there we go. And in this case, we're just going to have show address A. Um, I'm waffling again on just putting the entire definition in line. I can make show args separate and get this parameter list for all of these. And we can just say args equals that. So now args equals that string. And then this part can be done separately. So like down here, you'll just say S, there's the address, there's the operator, and then here is args. And that's what we return. Okay, I think that's reasonable. Let's leave this commented for a second. So here we just have show lit. And a space and then the show address. Right, and then this show is always just going, it's just deferring to whatever the show instance is saying. You've already defined elsewhere, specifically you've defined here, oops, how to show any argument. And what I'd like to do is just make this all derived. That can be like a follow-up refactor, but this doc here would tell us how to derive that. I'll share that in case people are curious. How to write a type class derived method. Deriving mirror. Sum of product of. Anyway, that can be something I review. I'd like to learn that. And maybe if I do learn that, I can bring that here and show it. It's certainly easier than writing like macros in Scala 2 for your derivation. It's like a top level thing now. Okay, so this one here. areg.name. And then we have a show lit. And then we have another show lit. So it's params. And we can make that the last param set the other things align. Sonar RMM. So we have just areg.name. And then we have a show lit type B. Any advice for a new student in this field? In what field? You mean just in like programming in general? I mean, if you're just starting out, all I can say is do a lot more of it. Keep programming. But if you mean like in the industry or getting into a particular kind of job, I know. Maybe someone has good advice. Ranzier, thank you for the follow. Okay, so we're showing an address. And then we're showing a lit. Show a lit. And in this case, it's a little bit different. We show a character. And how does showing a character work exactly? We basically do reg or lit. So we get value. We can get value as a lit. So a lit dot as character. And then that's it. That's my string, right? No. A, yeah, where do you referencing it? AD references are that value. Okay. Why is this a arg? We're pushing a value, right? Oh, hold up. We don't want to just show the value. So A just gets the value. we want to show the arg. So we're going to show an arg of address and do a arg, right? Something more like that. Let's go. When's the last time we were showing any bytecode? Okay, and when we have things like an out, yeah, we do want to get the register of that too. Interesting. I think we need a cast for character. Hmm. Okay, for now, we'll extract it manually. So we're going to have a reg.name, and then we're going to have parens, and then alit.ascar right in here. Okay. And show lit is actually show arg lit. We want to show the full argument. The arg. And show arg of address. The arg right here. Okay, show arg of lit. I guess we could have been doing like we'll find more places here. Okay, we can show. Oh, WMM. What was that supposed to be? BARG. Okay, let's find and replace lit with arg of lit. Right, that's what you want to show in the instructions. We can skip that one. We're doing that replacement. We're doing that replacement. And we're doing. Nope, we're not replacing anything there. So let's skip that. This replacement. Arglet, arglet. Okay. So this here is barg, and this here is carg. And this final case here, we just do the op. No op return or halt have no args. So yeah, that's empty string. And that leaves an unfortunate space here. Oh, are we still using A's anywhere? Oh, in addresses. So we got show arg of address. and an arg. Arglet, this is a barg. And anything else should be caught by no given instance for cast. You can't cast an arglet, so that's not quite right. Arg. Oh no. Arg. There's arglet. So that we could write. Yeah, or we could put it in show. We could do show. We could do show arglet here. Okay, that's I should have seen that from the start. So show, we just say lit after arg to say that it's a lit. Arg here is an address. Arg here is a lit. All of these shows don't need, nope, they don't need to type parameters. Okay, show this barg is a lit. Barg is an address here. Yeah, pretty straightforward refactor. Okay, so we're only showing args. This is an arg address. I'm gonna save myself a lot of typing there. If I caught that, but so it goes when it's late at night. Okay. Well, that should certainly be compiling. Not yet, not yet. Oh, yeah, random test code that we don't need anymore. Okay, and now emulator here. Value shows, not a member. State.show. Show instruction now. Dot show. Instruction. Invalid register index 57. Oh boy. Okay, I imagine that happened during my arg2reg and areg VM state in the emulator. Show instruction areg. So it's in our show instruction. VM state line 98. Not a valid index. So the thing we tried to parse is an index. It wasn't actually an index. So where was that areg used? Show instruction line 134. We expect this to fail. That's where it's checked. Okay. Right. When we do an output, So reg name a literal. A is literal. It was actually called a reg. Right. A calls that. No. A reg. A reg dot name. Oh, right. Um, that isn't right. A is not both a register and a literal. So let's look at the spec for out. A is oh right. We only do that if we have to dereference it. And sometimes we do have to dereference it. And oops, I do. Okay, so I think for this, we want to do something similar that we do to other args. To get that to work properly, to be able to have that be an arg of character. So we need to cast a character and a show character. Okay, so given cast character, w the word dot as car. Okay. Car required. Yeah. This returns a car. Now back here, we can do out the way we do everything else. And that is to show an arg. Oh, no. Show arg. Oh, that we are parsing as a character. Yeah, character is not a subtype of E15. Mm. Mm. Okay, well maybe we handwrite it. So arg dot match. Yeah, let's do it that way. I want it to give me my autocomplete. Okay, arg match. Arg of lit match. Here we go. Okay. So in this case, we do the whole parentheses thing from inst. it'd be kind of nice if I could get ASCII to fit into there, or the char to fit into there. And I think that upper bound of U15 is necessary. Okay. So we'll make it similar. Reg.name in this case, and A is when we've dereferenced it. A's are lit. We cast to the lit. Actually, A's are a character. Say CH. And then a show for CH. We don't need to do a show. We can just put that in there. CH. Okay. And regref registers. We can just do registers apply to reg over here. That gives us a word, and we can cast a word into a character. And I think we can just inline this here. Nice, nice, nice. And in this case, we just have b.as character. Oh, what's this reg.name? We can just do reg.name. Okay. Okay. So did we do everything we wanted? Oh, we didn't yet parse these into an instruction. That we can do, but when you call arg, when you call those args, we need to have a type parameter. You would have to match on the operator. Up match exhaustive. Alt is going to be an inst 0 of op. Set is going to be an inst 1 of op, and what is a set? Set A to the value of B. Let's just say it's an arg of U15. Set register A to the value of B. Yeah, I'm just gonna say those are both U15. Let's see what it is in practice actually down in our implementation set A register and then B U15 store. We're always storing literals. Okay, I think it's fine. It's fair to make that a literal because it's a register, and we only ever store literals. Oh, I guess this is a B arg or no, A arg. And we can say U15 because we don't know what's in there. And B arg of lit. Right? Is that working? Or an inst. Let's go to this definition. All of these should extend. Extends. Inst. And in that case, we need to do that. We need to pass along the op. Okay. I think instead of using the spec for reference, I'd rather use our implementation because we trust our implementation and our implementation has nice types. So halt has nothing. Push is going to be an inst one an arg u15 a arg u15. Continue margins for method apply and object inst. Oh wait, set. Set is an instruction with 2. It's an inst 2. Okay, push inst 1. Ideally, we just call show on an inst. But the problem is that the inst runtimes aren't there at, or the argument types aren't there at runtime. They get erased, and this argument here, we still need to operate this guidance. So we're still doing like some kind of duplicated work here, right? Do you see how like all this could be more generic? The show instruction, when returning it to string, we're using the same kind of information for this that we're using for this, right? We're saying that A is of type whatever, like it's an argument of type literal, or like it's perhaps a register reference to a literal. And then we're doing the same thing up here. And now we're about to do the same thing down here. So we haven't succeeded yet, but it's these 3 things. They all share that commonality, and that's what I want to abstract out. I want to abstract that out. so that, hmm, I think in order to do that properly, I'll need to sleep on it. So I might leave this for now. We'll make these triple question marks. This is an inst one of arg-15. Oh no, we also need the op. Maybe I could trust Copilot to bang it out. Maybe. Let's see. Let's see how accurate Copilot is here. So pop is going to be an inst. It's only ever using an a. So this is an inst one. Pop arg-15. Is that correct though? How did it know? Pop. Nope, it's a register. Okay, yeah, ChatGPT is just guessing there. And like we need something that is a source of truth. If we have something that's a source of truth, I suppose this is why we need like a differentiated AST. And we can't pass around the type parameters. Well, we can and we can't. I know. This needs me to like take a step back and do some thinking. And so I might think about that and bring that here if that's successful, if I find something. This is an A reg. Oh, right. But we have to say arg-15 because yeah, that's exactly what I would have done was arg-15. Because the argument is a register. Yeah, I'm trying to hack on a type where like really the types here is like there's an operator and then there's like 1 to 3 words. And how those words are interpreted depends on the operator. So if I want to have a generic instruction row, I think I might actually have to specialize to all of these and say that an and or an add, for example, is a register argument. It's only ever used as a register, so I don't have to do this arg-15 hack. And then there's a B and a C. And then we add the values of those B arg and C arg. So we also need to track like a reg reference distinct from arg. So our two reg, what I want to write here, so like we want a reg ref, and then the type doesn't matter, right? So we want the a reference. That's ideally what we're writing there. It messes my sleep schedule too. Okay, Copilot, how can you do here? Inst. Kind of inst. inst 3, op arg15, barglit, carglit. Okay. Copilot, can you do this? Okay, great. Those should all be similar. Inst1 op arg address. Okay. Oh man, I've been doing a lot of stuff that Copilot probably could have been done. Could have done. I apologize for that because I know some of it is a little bit circular. Okay. Instruction. If someone has attentive eyes, I wouldn't mind double checking over this. Because we can totally lie here. Like this is where we're making the spec. So this isn't being type checked against anything. Anything we write here is going to be taken as a word of truth. So there's nothing to compare it against except our knowledge of the spec. Okay. That should compile. Going to sleep at 9 a.m. and getting up at 5 p.m. Oh no, I might be doing the same. Error overriding value op and trait inst. We need the override modifier. And we already do that. Okay. Override val op. I feel like we went through this. We cannot overwrite val. Am I misusing the trait parameter there? You just need to know that any instruction has an op. Mm, okay, let's just do this instead. Def opcode, and take that parameter out there. Like, shouldn't that work? And then, oh, I suppose there's that override. There must be a field or method to name op in the superclass. of inst 0. Oh, yep. I forgot. I accidentally deleted that. Extends inst. Okay, that works. I wonder if I do actually need to override keyword. I feel like I shouldn't. So, okay. Yeah, that's how I expected it to work if it's like a parameter. I suppose I misunderstood. Okay, we'll go with that. We'll try just one thing real quick. We can undo it if necessary. Okay, what if you just pass along as a parameter? Oh, yeah, you could pass along as a parameter if it wasn't defined here. Unuse explicit parameter. Yeah, you'd have to make that valid there, and then now you're overriding. Okay, fair. That's how you want to express it. Starting emulation. Okay. There we go. Okay. We still have, there's still potential. There's still things to do with this here. But I can sleep on that. And I'll be back Monday. Geez, today's Sunday, so I'm not streaming tonight. But I will stream tomorrow night. Well, maybe I'll sneak on. If I'm just sitting around working and thinking about this, I might think about this there. But Monday tomorrow. Oh yeah, it's great that it has that self-test. Monday tomorrow, we'll go back to doing proper Synacor, and you can leave this digression alone. So we'll see. It depends on whether or not we use this. Depends on how far we get with that. I mean, it already exists. It already exists. We could already just use it. But whether or not we generalize it depends. Still not generalized. There's like structural, like semantic info that is duplicated between all these three, and that we want to get rid of. But yeah, like we need a spec. We need a spec, a source of truth that gives us this or this or this. And I think I just need to write. At this point, maybe I need to write a grammar. Essentially, is what I need to write. I should have just taken out like the big guns from the start. But it was still, I don't know, I think it was perhaps a worthy exercise. Let's find someone to raid. Which admin code? Oh, wait. Admin code's not going on anymore. We don't need to use that tag. Who all is on? Huh. There's someone doing admin code in German. Toggle bit doing the test stream, removing bugs from my programming language. This feels kind of similar in a way. Like we're writing an interpreter.
Copy. Open. I cannot open because I need to wrap everything with the context. right? So yeah, I guess I could write like the preprocessor to do
And
that
this is
maybe.
no camel. Cool.
But I think this one is going to be easier. We just say like this: let this be with context impl dot that, you know.
All right. Well, I appreciate all of you staying.
Ones are not like this.
While I try to make
such beautiful code. Yeah.
And yeah, I hope we can make it Monday.
Please use NeoVim. Come on.
Like
oh my fucking god.
Compiling stuff, and that will be
okay. If you say so.
That'll be the real stuff.
If you say so, let's go to NeoVim then.
All right. Have a good night or morning.
All right.
It's morning for pretty much everyone here.
Let's do that. Stu squared. Hello, hello. Thank you for the raid. Welcome, guys. How are you doing? How was your stream? What were you